Okay. So day 3, meteorology, basic weather studies continued. So today ultimately we cover, we're going to start jumping into pressure, units of measure, weather system characteristics, temperature effect, altimeters, pressure gradient force, kind of how all of that works. Then we'll jump into wind, states of matter, and clouds. So there's a lot of information in today's stuff. However, we're also, there will be plenty of time usually to talk about everything fairly in depth to the things that we need to, and but we'll cover everything today. Also, there are some like videos and things like that too that we'll watch. I believe on that, different ones that cover different areas of all of today's stuff. So I like videos. I think everybody likes videos. So bring this up. Trying to remember what was that a good view level?
Yeah.
Okay. So starting off here with atmospheric pressure and altimetry. So a lot of the stuff some of the stuff we'll read, some of the stuff we'll kind of just more discuss. But generally speaking, when we're talking about atmospheric pressure, I know you kind of got a little bit of an introduction yesterday. Those that were able to view yesterday's stuff so far have you kind of saw that there, the atmosphere has several different layers, and each one of those layers is associated with different types of pressure and different types of temperature and things like that. So obviously, primarily, aircraft movement and aircraft flying is obviously is we don't go too high. We don't go clear up into like the troposphere. We are mostly flying ground level up to really no more than 40,000 feet in most cases. So that with that said, the pressure pretty much within all of that area of the atmosphere that aircraft operations are conducted is all measured. It's all, there's different levels of pressure, but basically overall, the pressure that we're looking at, the kind of the history of it, is that the air, has pressure. Like it's basically, air pressure is obviously a way of measuring how much the air weighs, right? So whoever invented, in fact, I know they list it somewhere in here, but whoever invented the altimeter, or whoever invented, that's what the thing's called, with the barometer. Yeah, that's what I was looking for. With the mercury that goes, up and down, was able to basically kind of figure out that, that you can actually measure air density and how much the air weighs in a certain environment. And then they figured out, obviously, the different areas of the country, the air is less dense, more dense, some air, based on elevation, based on temperature, and based on water vapor in the air as well. So overall, how kind of this, affects aircraft operations is that aircraft, when you're at higher elevations and warmer temperatures, aircraft performance is degraded. So the most optimal settings for an actual aircraft to perform well is usually sea level at a cool temperature. So I don't know how many people in here have kind of seen, sometimes when we run into issues with, Denver is a perfect example of an airport where in the summer it's a really high elevation. Obviously, it's just above 5,000 feet, just above a mile high city. And on a really hot day in Denver, being the airport is 5,400 feet in elevation, and then sometimes when you get up to 80, 90, and even sometimes close to 100 degrees in Denver, it causes a lot of problems. And it's 100% related. Obviously, it has everything to do with the elevation, the temperature, but technically the effect is due to the air pressure density. And so aircraft, generally speaking, well, not even generally speaking, 100% of the time, aircraft performance is directly related to air density and how, basically how thick the air is that it's flying through. So aircraft performance is kind of it kind of goes backwards a little bit. This is stuff that kind of going back to what I said, we're going to be, I'll tell you ahead of time if it's stuff you need to know. This is the basic principles of this is definitely what you need to know. Kind of how aircraft performance works. So this is stuff you'll want to know, and this is a little bit more related to dispatch, but aircraft performance. When you're taking off and landing, you want the air density to be thick, basically, because the aircraft, basically, the denser that the air is, the more lift an aircraft can create. So, and it's the same thing when you're landing. So if you're rolling down the runway, you want that air to be nice and thick. You want a headwind. You want the wind blowing towards the plane, not, a tailwind. You want all of these different components together, to give the aircraft the best possible performance. So air density, temperature, elevation, and when you were looking at like how long a runway is and things like that. But going back to the example of Denver, on a really hot day in Denver, air density decreases with altitude. So the higher in elevation you are, the lower density you're going to have, generally speaking. There's a lot of things that affect air density. So, but when you're looking at just like a standard, there's a measurement out there that's just called a standard atmosphere. A standard atmosphere is basically where you take the same temperature and same pressure and you relate it at different elevations. So as an example, this is something you'll always want to know, but a standard atmosphere is based on, first of all, your elevation being sea level, okay, at a temperature of 15 degrees Celsius. So if anybody ever asked you what's the standard atmosphere, you would say 15 degrees Celsius at mean sea level, at MSL. So that one little thing, that standard atmosphere is going forward when we do flight planning and everything else we do related to aircraft performance later on in this course, is you're going to have to compare everything to standard atmosphere, because every aircraft performance chart that you'll see when you do manual flight planning later on, everything is based on standard atmosphere, and then what the difference is between your actual conditions compared to standard atmosphere conditions. So just as an example, and you have, well, let me go back. So you have your standard atmosphere that I just told you, and then you have another thing that's called ISA, okay? ISA stands for International Standard Atmosphere. And basically that is what the 15 degrees Celsius at sea level is. So that is considered, you'll hear it called ISA, okay? So if you ever hear somebody say, well, what's our ISA deviation, or what is ISA at our elevation, you'll hear them basically take, like, you always start out with your standard atmosphere as if you're at sea level, 15 degrees Celsius. Take St. George's as an example. Here we are 2,800 feet more or less above sea level, okay? So if our standard atmosphere pressure and temperature at sea level is supposed to be 15 degrees Celsius, then somebody might ask you, well, what is our ISA in St. George? Okay, It's obviously not sea level here, so we have to adjust for what it's supposed to be. So as you go up in elevation, for every 1,000 feet, and this is also something you'll probably want to write down, as you go up in elevation, every 1,000 feet should be a drop by 2 degrees Celsius. So if I'm at 1,000 feet elevation, then my standard temperature should be 13 degrees Celsius, and on and on and on. So as you increase in elevation, your temperature decreases by 2 degrees Celsius per 1,000 feet. And that affects that's if you stayed at the same pressure. Okay, so we're kind of what we're ultimately talking about here is standard pressure. So in order to maintain standard pressure, if my altimeter setting at ISA, at sea level ISA, which is the 15 degrees Celsius at sea level, the standard altimeter setting at that sea level would be 29.92. So put that down as well, 29.92. That is always your standard atmospheric pressure setting.
And that's at sea level?
And that's supposed to be measured as if you were at sea level, yeah.
So you enjoyed about 25?
The elevation, about 2,800. I think the airport elevation here is 2,800. 2884. Look at that. Yeah. Yeah.
It's kind of interesting last night, just talking about all this and performance and headwinds and whatnot. When American came in last night, they had 35 knot headwinds and they were able to stop at 84.
Yeah. Which direction did they land?
From one.
Oh, so they came in
They
from the south?
South and stopped at that first little spot. Normally they'll go to 82, but
yeah. Yeah.
I was relaxing. They were able to stop that far.
Well, and some of them, you know, I'm sure everybody in here that has flown on those flights will notice that, like, some pilots just hit the brakes until they stop. Right? Not everybody in here, I'm sure, likes stopping at the first turnoff. But, you know, when you're landing, like here in St. George, I'm trying to figure out if I should draw this, like, this direction. Let's just go as if we're looking at it from a horizon perspective. So if this is the runway, this would be, you know, the 19 end and the 1. So runway 1, 19, that's the runway is out here. But the pressure basically, so you know, you always want to land. So if you have a wind, if your wind is coming, you know, this direction, obviously, you know, I think most people know here, you always want to take off into the wind, land into the wind. That's always going to give you the best performance. So if the plane is going this way at 150 miles an hour, and then the wind is blowing this way, it's going to increase the indicated airspeed of the aircraft. So it's really weird to compare like a car, like the principles of how a car works as compared to how an aircraft works, because when people, at least for me, when I'm dispatching, it's hard for me to like, I've never like really flown, like I've flown like private pilot type stuff, you know, but I've never flown like, you know, in a jet where I have like thrust reversers and things like that. So it's really weird for me to like think of the principles of how an aircraft actually moves. If you think about it, you got two engines back up against the, you know, that are above the ground. Like if you think of a car, you got wheels that are connected to the ground that actually have force. You know, they're on the ground and they pull you because they're connected to the ground. But if the car obviously was in the air, the wheels would just spin and you wouldn't go anywhere, right? It's like the exact opposite science for an airplane. So, and this is kind of a little tangent, I guess, but as far as the way the wind and the speed of an aircraft work, in a car, you would never really want a headwind because it's going to degrade your gas mileage performance and things like that, and it's going to slow you down, and you're going to have to go faster in order to maintain 80 miles an hour or whatever you're doing on the freeway, right? So it's always worse to have a headwind, but for takeoff and landing in an airplane, that's exactly what you want, because if I need to take off, and aircraft have set speeds of, like, they rotate at an exact set speed, and let's say that speed is 140. Well, that speed is based off of an indicated airspeed. So, and we're going to get into airspeeds and things a little bit later, but indicated means what the aircraft thinks that it's going, okay? Performance-wise. That's what the aircraft, performance-wise, thinks that it's doing. But if it's in the air, and this is obviously where the headwind comes into play, if it's in the air or rolling down a runway and I've got a 20 mile per hour headwind, technically that aircraft can take off sooner, if that makes sense. Because the performance of the aircraft, it's getting an additional 20 miles per hour added, that really it's indicated at 140, but it's really only going 120, if that makes sense. Does that principle kind of make sense to people, how that works? So the performance is better. Now, if you have a tailwind, if you think about it, the exact opposite is going to have the effect. If the tailwind is going to make it, so if I had a 20 mile per hour tailwind, it's going to make it so that the aircraft really needs to go 160 to take off at 140. So that degrades the performance, makes it have to go further down the runway to gain more speed. And obviously the further down the runway you have to go, the more problematic that becomes, because eventually the runway ends, right? So same thing with landing. If you're landing into a 20 knot headwind, then you can technically land at a much lower speed. The aircraft still thinks it's going the speed that it needs to, but because of the headwind, it's really going slower and it'll stop faster. And that's kind of going back to what you were saying. 35 knot headwind, because of that comes off of the overall speed. It makes it so probably with fairly easily could turn off. And obviously if you go runway 1, that A4 turnoff is a lot closer than 19. But anyway, pressure-wise, it's the same thing. The more dense the air is, the more lift that's going to create. So as you're going down, if you're at a higher elevation, the less air there is total, the more, the further down the runway you're going to have to go to take off, because you're going to have to go faster to gather more air, gather more speed, and create the lift. So pressure, wind, all of these things calculate into takeoff and landing performance. Now when you're in the air, you want the exact opposite to happen. So airplanes try to fly as high as they can. And going back to the principle of the higher you go, the less dense the air is, that's why aircraft try to fly as high as possible. If they can go up to 39,000 feet, 39,000 feet is going to be much thinner, less dense air than, say, 30,000 feet. And the reason why they want the reverse conditions when they're at cruise altitude is because, if they're going through thinner air, then they can go a lot faster. So it's the same science for takeoff and landing, just flip-flop it for when you're at cruise altitude. Because at cruise altitude, you want a tailwind and you want really dense air, because you'll be able to go faster. So if that makes sense. When you're at 39,000 feet as an example, just to kind of give you an idea of how much of a difference there is, aircraft, even though they're flying clear up in the air, the indicated airspeed that I was talking about earlier is usually, at a really high altitude, is usually between 250 and 280 nautical miles per hour. So that's how fast, once again, that's how fast the aircraft thinks that it's going, but the true ground speed in those conditions is really more like 450 to 500. So it's nearly double the speed that it thinks it's going. So, but that's simply just due to how, little, air there is at that altitude. So now as they come down, that's why you guys probably hear us throwing it around, and I think sometimes you guys even ask, is there any way we could speed that flight up? to create less block for a legality situation. Well, one of those is going to be, can we fly higher? If we can fly higher normally, it's going to reduce block because it'll be able to go faster, and less fuel obviously is too. So in some cases that doesn't correlate because sometimes there's weather conditions going on where the headwinds at really high altitudes are way worse than say a lower altitude, but generally speaking, in a no wind environment, which is a lot of times when you're planning performance, that's how you initially plan. Everything we plan is based on, initially speaking, it's based on standard atmospheric pressures and no wind, and basically like a no weather environment. Okay, we do all that, we do all the planning, and then we adjust everything after the fact for actual conditions. So going back to the standard atmosphere now, back off of my tangent here for a little bit. Atmospheric pressure, so the temperature decreases for every 1,000 feet. So like say here in St. George, 2,800 feet, you'd probably round that up to 3,000, but just for the ease of calculation. So you would be like 9 degrees Celsius, should be more or less what the standard atmospheric temperature should be in St. George if, like this is going back to the thing, if it was a standard atmosphere. We almost never have standard atmosphere though, right? If everybody can think about it, like St. George is a lot hotter than some areas. If you take a 2,800 foot elevation area in, gosh, who knows where, in let's say Washington, along the coast, it's definitely not going to be comparable to 2,800 feet in this southwest desert climate area. So the fact that we plan everything with a standard atmosphere is just simply to kind of like get us going for performance, and then we always, after the fact, we always adjust for, okay, well this is what it's supposed to be, and then this is what it actually is, okay? So today, let's see, just to kind of give you an example, let me jump into this other little thing here. Go into, I was going to bring this up anyway.
On that, what's the difference between the standard atmospheric pressure and the international standard atmosphere?
Well, so what I should have said back, ISA is standard atmosphere. So you'll hear somebody refer to standard atmosphere, and that is what ISA is. So it stands for International Standard Atmosphere. So it's the same thing. It's basically what I'm saying. Yeah, exactly. So you'll hear ISA. Like, what is ISA supposed to be? At like here in St. George today, and you'll see this a lot later. So if you don't fully get it right now, don't worry about it, because we're going to really get into it later with planning and things like that. But I just wanted to show you kind of just quickly to kind of give you an idea of how it works. St. George Regional today, you guys can all see this, right? On the far right side here, right now we're 51 degrees Fahrenheit, 11 degrees Celsius. Okay, so we're at 2,800 feet here. When you are talking about aircraft performance, you always lean on the side of penalizing it more than helping it. So we always, if we get into a situation where we're going to round, and you'll notice with manual flight planning and stuff, there is a lot of rounding, but you always round to whatever penalizes the aircraft more than obviously help it, right? So that like this, like back to what I was saying, so 2,800 feet elevation, if this were a standard atmosphere here in St. George, it should be 9 degrees Celsius. Right now it's 11 degrees Celsius. So it's slightly warmer than what ISA says it's supposed to be, if that makes sense. So right now we're 11 degrees. We're 2 degrees warmer. right now in St. George, and this is where you'll kind of hear this referred to later on, but right now St. George is considered ISA +2. Okay, so later down the road, when we talk about standard atmosphere deviation, or if you ever hear the term ISA deviation, that is what we're talking about. Like, what is St. George's current ISA deviation? Well, you would look it up. You need the elevation and you need the temperature to figure that out. And right now, knowing that St. George is 2,800 feet, it should be 9 degrees Celsius. It's really 11, so that means it's ISA +2. So when you get into performance charts later on, you'll see that there are performance charts based on what ISA is at the airport you're wanting to take off and land at. So there's an ISA chart that if it just happens to be ISA, exactly what it should be, you know, and sometimes you'll see that. If it happens to be ISA where you're trying to take off from, then there's a chart for it. But then there's an ISA +5, there's an ISA +10, ISA +15, +20, +25, +30. In a lot of cases in St. George here in the middle of summer, you get into ISA +45, which is like the absolute highest you can get. I know you guys have all probably seen, and probably not Jake, but you've probably heard and seen of some of those days in the middle of summer where we can't operate because it's too hot. Has anybody ever seen that? Like in Phoenix. It happens in Phoenix. It's happened here, but it generally happens more in Phoenix is probably the most common. Like, it's simply too hot to operate. And that's because that happens because of the ISA deviation. That's what it's calculated off of. It's not an exact temperature per se, but the CRJ 700, right? The highest chart that you have for a CRJ 700 performance-wise is an ISA, I believe it's +40 or +45, one of those two. But either way, if you exceed that, then it's just considered you can't operate because you don't have the numbers for it. It's basically what it's saying. There is an exact temperature that we use, but when we're doing manual flight planning, we round. So if it's ISA +2 in St. George, we would use the ISA +5 chart because ISA +5 penalizes it a little bit more. We couldn't use ISA because it's not quite as good as what ISA should be, and it's not quite as bad as ISA +5, but when you have to pick between the two, you have to pick the one that penalizes it more. So the higher you go, the higher the penalty is basically what it does. So does that kind of make sense, everybody? Yeah.
I just have a question. So does SkyWest go more for the mercury or hectopascals?
As a dispatcher, we really mostly just look at the mercury scale. And
Because
then,
I noticed it has the hectopascal right there. It doesn't say mercury, so I was just curious.
oh yeah, so if you look down here though in the actual METAR, you see right there A 3007, and we'll get into weather reports later, but and that's really more because we're a U.S. regional airline. Now, if this were Delta or United or whatever, and you're doing a long-haul international flight, then yeah, you probably as a dispatcher would be more in tune to using like sea level pressure and these other ones that we're going to talk about here in a minute. But generally, here we're flying U.S. to U.S. domestic operations, so pretty much everywhere we go and fly to is going to have an actual altimeter setting based on inches of mercury, which is what I think probably most everybody here is most used to, those of you that look at the altimeter every day, if any. So, so with that, let's jump back into this. Okay, so atmospheric pressure is one of the most basic variables used to describe the state of the atmosphere and is commonly reported in weather observations. Unlike temperature and relative humidity, changes in atmospheric pressure are not as readily sensed by people. So, yeah, kind of just going back to what I was saying, it's not, you know, pressure changes, sometimes you can actually feel, you know, sometimes you can step outside and you can kind of, you know, feel, you know, it'd have to be very dramatic, but generally speaking, you can't really go outside and tell, oh, air feels heavy today. or whatever. So variations of pressure across the earth are associated with pressure centers, either high pressure centers or low pressure centers that cause the wind to blow and can bring important weather changes. Density, which is directly related to pressure, is a property of the atmosphere which can be used by pilots to help determine how their aircraft will perform at various altitudes. This chapter discusses atmospheric pressure, how it's measured, how it varies across the earth, and covers the altimeter, which is a pressure sensor used by pilots to determine, I hate this thing, to determine altitude. Finally, density will be discussed along with its relationship to density altitude. A lot of this I'm not going to try to read verbatim, just because it gets kind of boring, but it basically is talking about how the air is made up. I mean, molecules and atoms and things like that. That's not necessarily, you don't gotta you're not considering any of this when you're dispatching, so we're not going to really talk too much about it. But as long as you have a general understanding of, how things are made, between atoms and molecules, and that the air is full of them, and, the more molecules and atoms in the air, the more dense it's going to be, and the less dense it's going to be. As long as you understand how that works, then we're probably fine on this particular section here. And that obviously all of that relates to the weight of the air. And the weight of the air is the density of the air. So all of that and kind of what we were talking about is air density. The only thing in here is since molecules move in all directions, why does it do that? Since molecules move in all directions, they even exert air pressure upwards as they smash into objects from underneath. Air pressure is exerted in all directions. So that's just one thing just to remember with air pressure. It's not like it's weighing down. It's pressing in all directions. So, if a plane is flying into it from this way or this way or this way, it's going to be the same pressure regardless. Okay? Atmospheric pressure is the force per unit area exerted by the weight of the atmosphere. Since air is not solid, we cannot weigh it with a conventional scale. This is basically where it's jumping into talking about this guy, Evangelista Torricelli, who proved he could weigh the atmosphere by balancing against a column of mercury. That's where the barometer was invented. He actually measured pressure, converting it directly to weight. So that kind of gives a little demonstration of what he did there, that 5-1. Anyway, as long as you have a general idea of how air is made up, most of that really isn't too important. Barometers, that's the instrument that he designed to measure pressure. It's used in the aviation community. This just describes how a barometer works. You don't necessarily have to know how a barometer works, you just have to know how to read it. So as long as you understand that barometric pressure, the higher the reading, the more dense the air, the lower the reading, the less dense the air. That's really all it comes down to for you guys and for dispatching. Pressure units. Atmospheric pressure is expressed in many ways throughout the world. Meteorologists worldwide have long measured atmospheric pressure in millibars, which denote pressure as a force per square centimeter. However, after the introduction of the International System of Units, the hectopascal, thing that Marin was mentioning, was adopted by most countries and is used in the Aviation Routine Weather Report, a METAR. And we'll talk about METARs later on, but aviation selected special weather reports. So it's used in METARs, like standard METARs, and then speci METARs. And like I said, those two things we'll talk about later on, but they're just the aviation. Some of you guys probably already know what they are, but that's just the hourly weather report that comes from an airport. That's all that is. So every hour, an airport is supposed to report what the conditions are. That last little thing that I brought up in where we were looking at the St. George weather, that all was basically that was the latest METAR for St. George. Airports are scheduled to issue a METAR every single hour, and when they issue that, the only way that they're going to, if basically in between those, like this hour and the next hour when the next scheduled METAR is, the only reason that they would ever issue another one before the next one is due is if a certain criteria of that weather changed. So there's a lot of things, like if it would have to change, like the visibility would have to change by so many miles of visibility, the ceiling would have to change, the wind, if it changes more than like 30 degrees, you know, things like that. There's a whole set of parameters, but then if that happens, then the airport would then issue kind of an immediate report to kind of show, hey, the last one that we basically the last one that we reported is no longer really accurate. So they sometimes will issue one kind of in between, and that's only if enough of the parameters changed during that time. So, but just to kind of give you an idea of what that is. Let's see. The unit inch of mercury is still used in the United States for altimetry. So you can see there that's what we still use here, kind of the typical US thing where we still use our own scale. You know, we haven't gone to metric or anything. This next one here is just talking about the units of pressure based on the different scales. So in a METAR in the United States, you'll see the actual altimeter setting, but every one of those METARs also has the actual millibar setting, usually later in the METAR or towards the end, and sometimes it also has the sea level pressure in there. So usually the other scales are available in a METAR, even though you don't necessarily always use them as a dispatcher. They're still usually in there. Let me see if I can... Okay, so as an example here, if you can see on this bottom right here, that's the latest St. George METAR down there. It was issued about 10 minutes ago. It's always issued right before the hour. So, but the altimeter setting was 30.08, and so you can see that A3008, that's the altimeter setting. But then later on here, this SLP stands for the sea level pressure, and that's basically giving you the setting in sea level pressure as well. So, and then up here in this top part, normally you don't get all this. You see how the temperature now increased to 14? So it went from 11 to 14. So now we're sitting at ISO plus 5 in St. George, just to kind of keep tracking it. We do, going back to the Celsius and Fahrenheit scale, the one thing we do in aviation is we use Celsius 100%. It's kind of crazy, like the things we decide to use and the things we don't. Like, you know, we still are going to use the barometer, inches of mercury, but we're going to use Celsius. You know, it's like mixing and matching whatever we like, I guess. Okay. Station pressure. The pressure measured at an airport is called station pressure, or the actual pressure at field elevation. Pressure is lower at higher altitudes, which we already talked about. Therefore, airports with higher field elevations usually have lower pressure than airports with lower field elevations. For instance, station pressure at Denver is less than at New Orleans. Makes sense. The next few subparagraphs will examine some factors that influence pressure. So this is kind of obviously given the scale there. Everybody can imagine, you know, Denver being higher than New Orleans. Pressure variation. Atmospheric pressure varies with altitude and the temperature of the air, as well as with other minor influences such as water vapor. Pressure changes with altitude. As we move upward through the atmosphere, the weight of the air above us decreases. If we carry a barometer with us, we can measure a decrease in pressure as the weight of the air above us decreases. This is basically just showing, as an aircraft flies higher, the air is less dense, which, going back to what we were talking about earlier, as an aircraft goes to cruise altitude, you try to get as high as you possibly can in order to get into the less dense air to have better performance, better fuel burns. These standard altitudes are based on standard temperatures. So kind of this is just going back and talking about the ISA stuff. So standard altitudes are based on standard temperatures. In the real atmosphere, temperatures are seldom standard. So we will explore temperature effects on pressure in the following subparagraphs. So temperature effects on pressure. Like most substances, air expands as it becomes warmer, and it contracts as it cools. I figured the next one down. It shows 3 columns of air. Let me just go to it. So this is basically showing 3 different columns of air here. And one is showing how the temperature, like it's the same, these 3 columns are the same pressure. It's just that because of the temperature, this one shows a lower altitude. This one shows kind of more of a medium standard atmosphere, and then the warmer temperature shows it as being higher up. So basically what this is ultimately getting at here is, if I'm in St. George, once again, we'll keep using the example of St. George, but if I'm in St. George, the altitude, the way that the pressure reads, if I came here and I set, if I'm in an aircraft and I set the thing is, when you're in an aircraft, you can adjust your altimeter setting. So you can see in the METAR what the true altimeter setting is, and right now it was the 30.08, but in an aircraft I can actually get in there and I can adjust it to a different altimeter setting. So when you're in an aircraft, if you want to know what the pressure altitude is of the airport that if you're on the ground here in St. George and you want to know what the pressure altitude is, then you simply take your altimeter and you put it at 29.92, which is the standard atmospheric setting, right, that we already talked about. Now, because of that altimeter setting, it will then adjust your actual altitude. You'll see your altitude fluctuate on your altimeter. So the altimeter is what measures the height above sea level, essentially. But when you're adjusting that, if you set it at the standard atmosphere, you'll see that the altimeter will increase. So if St. George is supposed to be at 2,800 feet, and then you set it to 29.92, and it's really warmer here, you'll see that altimeter actually show you as being higher than what it really is. We're going to get into talking more about this right now, but just to kind of describe, outside of the way this describes it, a little bit of how it works. Warmer air, when it's a warmer temperature like it is right now, we're at ISA +5 in St. George, because it's warmer than what it should be, it's going to think, the aircraft is going to think that we're at a higher altitude than what we really are. And that's what this little figure is supposed to show. So if it were standard, you would be at the medium. Colder air makes it think, if we were ISA -5, it would think that we were lower than what we really are. It would think that we were like at 2,400 feet in elevation. And the warmer ISA +5 makes it think that we're at like 3,200 feet. I mean, I'm just throwing out figures as an idea, but the standard one is, if it were exactly what it's supposed to be, it would show the exact elevation, if that makes sense. Is it confusing, kind of this? I don't mean to like get kind of, I know it's all kind of garbage sometimes, but basically, if St. George was sitting at ISA where it was supposed to be, and you tuned your altimeter setting to 29.92, it should show you the exact true elevation of St. George, okay, if that makes sense. When it's warmer and you tune it to that, your altimeter will adjust it for temperature, but it'll actually show, it looks like that you're higher. And then the other one, you know, if it's colder, it'll show you that you're lower. So altimeter settings do play a really important role when you're taking off and landing, most specifically when you're landing. Because if you're coming into an airport and you don't adjust your altimeter to what the METAR is reporting, then the aircraft is going to think that it's higher or lower. And we're almost never at standard, right? It's very rare to be exactly at ISA. Hardly anywhere is ever exactly at ISA. So if it's not at ISA and you don't adjust, then, you know, if you're coming in, obviously you can see things, but the airplane is going to think that it's lower than what it really is if it's colder, or it's going to think that it's higher than what it really is, which is obviously the bad one. You know, if your plane is telling you that you're 400 feet above the ground, but you're really only 200 feet above the ground, you can see the problem, right? So it's important to obviously know the correct altimeter settings. Sea level pressure. Since pressures vary greatly with altitude, we can't readily compare station pressures between stations at different altitudes. To make them comparable, we adjust them to some common level. Mean sea level, MSL, is the most useful common reference. In figure 5.6, pressure measured at a station at 5,000 feet elevation is 25 inches. Pressure increases, and this is one that you'll want to know right here. Pressure increases about 1 inch of mercury for every 1,000 feet. It kind of goes back to that same thing. Temperature decreases by 2 degrees for every 1,000 feet. Pressure increases 1 inch of mercury for every 1,000 feet, for a total of 5 inches. So if you're 5,000 feet elevation, you should it should be 5,000 feet. Sea level pressure is approximately 25 plus 5, or 30 inches of mercury. Sea level pressure is typically displayed on surface weather charts. Pressure continually changes across the Earth, so a sequence of surface charts must be viewed to follow these changing pressures. So this is going to jump into discussing like when you're flying. This is more related to like a private pilot type flying, like somebody that's flying in a Cessna at a lower altitude. It doesn't really relate to the commercial airline flying, because generally speaking, in a commercial flight, the dispatchers mostly always work with, a plane takes off at an airport and it normally climbs straight up really high. Once you get above 18,000 feet, you set your altimeter to the standard atmosphere, which is 29.92 once again. So the reason why you do that is the altimeter setting is really only important as you're leaving or approaching an airport. If you're at cruise altitude going, several hours away or whatever, then if we're above 18,000 feet, we really don't care what the altimeter setting is, because as long as we know that we're 18,000 feet or above, we're going to clear every obstacle, height-wise in the United States. So here in the U.S. and for regional flying, once you hit 18,000 feet, part of the checklist for the pilots is change the altitude to 29.92. And then they leave it there. And the reason why they leave it there is so that all other airplanes, as you know, the airspace is very busy, right? So any aircraft, whether it's ours or Delta, United, any airplane, regardless of size, every one of them goes to the standard atmospheric pressure once they hit 18,000 feet. The reason for that is because if they didn't, then let's say they left it at the at 30.08 if you left here from St. George. If you left that altimeter setting above 18,000 feet, then your plane is going to think that you're at a different altitude than what you really are. Well, it'll be at the altitude you really are at based on St. George. However, all of the other planes that are flying around, it's important that if you're above 18,000 feet that everybody has the same pressure setting. The reason being is because once you get up to higher altitudes, planes fly closer together. Like if I'm going, I might be going west at 38,000 feet, passing a plane that's going east at 39,000 feet. Well, if I didn't adjust my altimeter setting, I might be 500 feet closer to that plane, if that makes sense. I might be at 38,500 because I didn't adjust it. And so you can obviously see the problem, especially if the altimeter setting was pretty dramatic. If you're at, if you think about 1 inch of mercury is 1,000 feet, and let's say you had an altimeter setting of, 28.92, which is not uncommon, or let's say you had 30.95, which, not uncommon. Like I said, those are expected fluctuations depending on where you're at. But if you didn't change it, that's 1 inch. I mean, that's literally 1,000 feet difference when you're up in the air. So it's important that above 18,000 feet, everybody has the same altimeter setting so that everybody is reading the same altitude. Basically, that's what that's for. So that we don't crash. The only time once you get below 18,000, then you do want, if you're coming into Salt Lake, then you want to adjust it. Once you're below 18,000, you want to adjust it for whatever airport you're going to land at, whatever their altimeter setting is. Now, if you're in a general aviation plane and you're taking off and flying in a Cessna from here, but general aviation, you don't ever get to 18,000 feet. They're not even pressurized aircraft. So you're flying between 5,000, maybe up to 12,000 feet, depending on where you're at. But they're never getting high enough to where they would adjust to standard atmosphere, basically. That's really just for commercial jets and people that are flying higher. But if you're flying lower, and I'm flying, in a Cessna by myself from here to Salt Lake, then those people, when they're under 18,000, all along their route, they are adjusting their altimeter based on where they're at. So they take off from St. George with whatever the altimeter is here. Once they get to, say, Cedar City, they tune into their weather, and then they adjust it for Cedar City, and then they adjust it for Parowan, and then they adjust it for Beaver. So the whole route, they're adjusting it constantly so that their altimeter is reporting the correct altitude, because the pressure difference can be even just between here and St. George, as everybody, or between here and Cedar. I mean, it's almost 3,000 or 4,000 feet difference just in elevation. So obviously the altimeter setting is going to be really different just in the 50 miles between here and Cedar. So if you don't adjust that as a general aviation person, then you're going to be way off on your altitude, is basically what this is saying. But overall, the idea here is just to understand how the altimeter and how the pressure works in an airplane. So let's see. Okay. Sea level pressure analysis surface chart. After plotting sea level pressure on a surface chart, lines are drawn connecting points of equal sea level pressure. These lines of equal pressure are isobars. Hence, the surface chart is an isobaric analysis showing identifiable organized pressure patterns. 4 pressure systems are commonly identified, and everybody's probably heard and seen these: low, high, trough, and ridge. And this kind of explains what they are. A low, a minimum of atmospheric pressure in 2 dimensions on a surface chart, or a minimum of height on a constant pressure chart, also known as a cyclone. So when everybody looks at, across the map, and I'll bring one up here on the weather thing here in a minute just to see what we have currently out there. obviously our air masses out there are made up of low pressure systems, high pressure systems, and then you have troughs and ridges. But we'll look at each one of these. So a high is a maximum of atmospheric pressure in 2 dimensions on a surface chart, or a maximum of height on a constant pressure chart, also known as an anticyclone. So when you say a cyclone, does everybody know what a cyclone is? Or I'm sure everyone's heard of a cyclone, right? So a cyclone is basically just air that is rotating counterclockwise. Okay? So if you look at so the low pressure systems are what we associate with all of our adverse weather. Okay? Hurricanes, typhoons, all those types of systems, thunderstorms, all of those things are associated with low pressure systems. And low pressure systems, as they're moving, they're spinning counterclockwise, which is what a cyclone is, counterclockwise movement of air. So I'm sure if you've seen, like, when you're watching the Weather Channel or whatever, and you're watching the progress of a hurricane moving towards whatever, they always show it spinning, right? Or if you do the fast motion satellite imagery, it just shows it going like this. It's always moving. You'll always notice it's moving for me, counterclockwise. So that's associated with a low. Now a high is exactly the opposite. High moves anticyclonic, so it moves clockwise, spinning rotations. But the difference between a high and a low, obviously, is high pressure, all of your air is going to be really high up in the atmosphere. And a low pressure system is going to be more concentrated down towards the ground, which is obviously, when you think about weather systems, and you think about like rain and thunderstorms and hurricanes and things like that, they're usually low pressure. Well, they're always low pressure systems, but associated with low pressure would be where you have low-lying clouds, wind and stuff like that, reduced visibility because it's foggy, or you have rain or whatever, So when you have a high pressure, it looks just like it does outside right now. The clouds are way high up in the sky, blue sky. There's nothing reducing our visibility out here. Moving over to a trough is an elongated area of relatively low atmospheric pressure, and a ridge is an elongated area of relatively high atmospheric pressure. So troughs and ridges, we'll look at them here more in a minute, but sometimes you get a low pressure system which moves over an area and it just sits there. It doesn't move. It can't escape. Sometimes you think of that as like, as an example, like, like Salt Lake sometimes in the winter, like you'll get an inversion, and what'll happen is, the low pressure system will come in to the valley, and it's so low, and since it's associated with the low, it can't escape. Basically, it can't, it's got mountains on this side, mountains on this side, and there's other areas of where troughs exist that are non-mountainous, but it's a really good example because you can all see how it works. But it's a low pressure system that ultimately what happens is, because it's trapped in between the mountains, eventually a high pressure system overtakes it and moves over the top, but it traps the low pressure underneath it. And since it can't escape, and since there's a high pressure sitting on top of it, it just stays there. And you get the bad visibility, you get obviously the bad air quality because of the contaminants can't escape, nothing can escape. And that's kind of what you have with a trough system, is just an elongated area of low atmospheric pressure that is not moving. Generally it doesn't move, and sometimes it'll move a little bit. You also get these along coastlines a lot of times, like sometimes like when we get really bad San Francisco flow programs, it's because a trough system is sitting right on the coast, and that is causing the fog and the low-level ceilings to just stay there, But we'll look at them all a little bit more here. Ridge is exactly the opposite of a trough. This is a constant pressure chart. So when you're looking at these charts, you see all these lines drawn everywhere, and you know, in most cases they don't. You're not, as a dispatcher, it's not like you're constantly looking at a chart like this. You really hardly ever are. But obviously, all this is just showing us is just, you know, where a high pressure systems and low pressure systems exist. I was going to jump into our map over here just to see what today looks like. Let's see here. So this is looking at a chart. This is today. Let's see. Does that show up very big?
Yeah, it looks really fine.
Is that better?
Yeah, it's bigger.
Okay. So just looking at this here, you can see, you know, all your H's are highs. All these lines like this here are troughs. And you can see where troughs exist here. So troughs are often associated with, like you see this high pressure here, and then you see a high pressure here, but you see a trough right here in the middle. This is happening simply because this is being caught in between two high pressures. So troughs, kind of like I was saying with the inversion, sometimes troughs get caught underneath high pressures, or they, most generally speaking, they get caught between high pressures. So, you know, and it just, a lot of it just depends on the topography of whatever land it's over, you know, in most cases, kind of like Salt Lake. But that's how you'll often see them, you know, in between a high pressure, or sometimes, you know, in between a low and a high, but they're generally in between pressure systems. You can see down over here, like here's an example right here, kind of what I was just talking about earlier. There's a trough sitting right along the coast of California. So, you know, based on this, you know, we should probably pull up, you know, just to kind of see some of the coastal cities in San Francisco, or, you know, along the California coast, just to kind of see what kind of weather phenomenon that is bringing. We can look at them in a minute, but yeah, other than that, you can see the low pressures, and you can see, you know, a lot of these boundaries, like these frontal boundaries here, and we'll talk about fronts later on, but you can see the bad weather obviously here, the radar, the green, the thunderstorm lines. I mean, that's usually always associated with, you know, low pressure systems that are moving. Well, the only other thing I wanted to bring up here was radar. Let's see if I wanted to bring up, see if I can bring up some looping radar. I don't know if this is going to be a very good one. It's a lot easier to see like when you're at work, but it's probably not showing up very good for you guys because of the connection. Let's see what this one does. Is that, when this shows up, is it showing up very good at all, like where it's spinning?
Well, yeah, it's a little choppy, but
Not as choppy as yesterday or last time.
Yeah.
No,
Okay.
sorry, though.
Yeah, and so I mean, there's the thing is about these systems is that like you can see, so there's usually several pressure systems, like this whole thing along, you know, the the central U.S. there. It goes from like Kansas all the way over to Pennsylvania. That is going to have several low pressure systems within it, and so you'll actually see like several individual systems within that whole system turning counterclockwise. The system as a whole is still moving from west to east, but within that, it's kind of like the Earth, you know, a little bit like the Earth rotates and then it also orbits. So it's rotating as it orbits kind of at the same time. The weather systems are kind of a little bit the same. They're always moving usually from west to east generally. So they're moving, but as they're moving, they're also spinning, you know. So anyway, we don't, you know, we're not meant to get too in depth into this because we'll look really in depth at like satellite imagery and stuff later on. But just to kind of give you an idea, and then like some of the high pressure systems, you know, you can see them moving counterclockwise, clockwise. But the one that I can kind of see that's really pretty good is this one right in this area over New Mexico and Colorado. You can actually see it, the outer edge of it spinning counterclockwise. But you have to actually have the clouds, you know, in order to obviously have the visibility on it. So it sometimes it doesn't show up as good as I'd like. Anyway. So yeah, so these lines are just connecting equal lines of pressure. So they, you know, they'll obviously, when you connect equal lines of pressure, so if it's 1016 millibars down here, and then it's 1016 up here, you can kind of see this whole line is following that same pressure level. So the 1016 level is going like this, and then when you map these equal lines of pressure out, that's when you'll be able to see, you know, you can actually see how they're rotating, and you can actually see the definition of the highs and the low pressure systems. So not, you know, like I say, we don't really get too in depth onto any of that stuff or even really look at it that much, but just so you know what it is, I guess. This next little part is just talking about the National Weather Service and kind of what it does at each of its National Weather Service locations to, you know, figure out pressure and stuff like that. They send these balloons up into the air, which will take it'll take radio gear, sensing elements, and it'll get the wind speed, the direction, and it'll track the balloon with the GPS to kind of see where it's moving, and it'll take those pressures, and that's how they ultimately make these maps. So all these National Weather Service systems, they usually send up a balloon every single day or so many times per day, and each one of those National Weather Service stations compiles all that data, and then they send it, and then, you know, the National Weather Service as a whole compiles it all and makes these charts. So that's kind of where they come from. That's what the balloon looks like. But they're just taking different readings, and they take a reading at this altitude, a reading at, you know, another higher up altitude, and they map out all of the different pressure levels. And all those lines that you see on that chart are called isobars. Let's see, so this one is, so it's just kind of just giving us an idea of the different levels. So this is like a 500 millibar constant pressure chart. The last one I looked at was like a 1000 millibar constant pressure chart. So it's just showing you the different levels, you know, and the different levels, you know, depending on what you're looking at, will show more defined areas of lows and high pressure charts is basically all it's really saying. And, you know, at certain levels, it'll, you know, once you get really high, it'll show you, you know, like your ridges and your troughs. Well, really high when you get the ridges, you know, since a ridge is a high pressure. But this next little thing is just kind of showing like the relation in how many feet. You know, so 500 millibars is roughly 18,000 feet. So this isn't, you know, stuff that we really care too much about. Does anybody need a break? Sometimes I kind of lose track of time. 10:40. Let's just take a break real quick. Kind of gone over the time that I normally would take one. Just say 10 minutes or so.
Take notes, obviously not in case it has to be remembered to write it down.
Right, yeah. I tend to know things about writing things down.
Yeah.
Good work.
Boring enough yet? Is this working okay, you think, as far as that following along on the? Yeah. Trying to get that projector working. Come in and talk about that.
I mean, it almost seems a little bit
Better?
easier, yeah, because, with all the extra light outside, it might be harder to see the board.
The only thing that I think that would be better for is if I have a video going.
Yeah.
You know.
So that, is that the next monitor that you were showing, or, oh no, NX is maintenance? So, do we have access to that as well on SkyWest Online, or do you have like dispatch?
There's specific things that only dispatch can access. I'm not sure on this specific thing though.
Gotcha.
You'd just have to get in there and I guess see if you can get into it.
Where would I go?
It would just be under the operations tab. And then it'd be on the right side and it would say weather reports.
Okay, and then I can just, well, let's see, it's got a spot for doing a release.
Yeah, look down below that. Okay, weather reports.
The ATAC system thing, or
Just that weather reports. Oh, so yeah, it just takes you to that. And automatically takes me to the previous side. So, yeah.
so I'm guessing that on here at least you can see the low pressure and the high pressure.
Yeah, and you'd have to change the chart, but you get into, let's say, go up so you can see the options. Just go to, go up more. So go to like the observations. Let's see. One of those should take you to like one of the along in here. I'm not sure which ones. I gotta get into the hardly, but the forecast ones. Okay, so look at like the product charts. That's chart, but not current. Right. Oh, no, this should all be current.
Oh, okay.
Oh, well, that's not showing anything, but that should have stuff on it, but
Go to red level. Yeah, I don't know. Yeah. Little problem home. So, it's a little level. Yeah. It's great. Have to get into it. Satellite. I might show it if it has to.
So I'm in Jackson, would that be a ridge? Just a bit of the
To cover up with.
Where it comes over that ridge, it's there in Canada Park, but it's,
Yeah, I brought my.
I mean, it's relatively low, so it's at like a big.
I brought mine. Yeah.
It can be a combination of, the biggest thing about an emergency is that all of
Otherwise,
sometimes traffic just the air that's
the
already
constant
there.
been
The big thing about
Of course, there's no stools floating around.
high pressure is sitting on top of whatever air mass is in the valley, and then it's not letting it escape. So if you have, like for instance, sometimes it's salty, like if you're in the ocean, because let's say maybe it was not low pressure that was in there before, like but it's just regular high pressure comes over the top.
Next time you can write, this is my last.
Yeah.
So can't escape, so what happens is that all of
It's like the rest of the
pollutants
Don't
just
touch
collect,
my
and
wrist.
that causes like a pollution. But then there's the other type
Oh, yeah?
where it's already like.
You remember Al?
like-
Oh wait, didn't he like eat your stuff?
And then all he would do,
Then-
really good.
No.
Yeah, it's really
So right here.
the opposite section. I was sort of crying, I was so mad. Scope of angry.
Yeah, look at your cute little jacket.
Okay, well, technically, not mine.
I don't believe that for a second, we're supposed to be in the 90s.
Yeah.
Only sort of warmish thing.
I feel like you should put it on, take a picture in. It's adorable.
Do I fit like 6-year-old pipeline?
Yeah.
All right.
One of those tests in life, you know?
Yeah. Lose too much body heat in the process.
Was it about to leave anything that was about? No.
Yeah.
So what time are you working tonight? They're gonna figure it out, and I told them I
It's
have
like
to
this
work
one,
5 hours.
this is how they for junior man, it was C3, but for the 2 it's 7.
Okay, that's what I told them,
Which,
but they're like, that doesn't make sense.
it doesn't
And I
make
was like,
sense.
that's what she told me. That didn't make sense.
And my birthday,
called
granted
sick
vacation
after you
last
left.
minute. Yeah,
Oh, no, he called and said, I took the phone call. And
Oh, yeah,
I
that's
went over
right.
to Jolie, but then I left, yeah.
That was right.
Yeah, I have no idea, like, what the shit like people like me over there from 2 to 5 and then just be somewhere for 2 hours. Like,
They had to have, Shauna supervise yesterday.
it's trying to see.
They had Shauna, yeah, come off the wall to supervise me. There's no shift we've done. That's like bottom of the bucket. Throwing me.
Who all called in then? Everybody?
Marianne,
Marianne
and
did.
Grandma's been sick, and then Oli has been in and out.
Oli only worked like a half shift. Marianne came in for like 3 hours and then left. So then that's when Shauna got in at 8, and then Shelly had to take the other spots. I don't know who it was, but they had Shelly and Shauna supervising, and then Oli came in like halfway through. It was just like ragtag.
We were talking about Marianne's heart attack a couple of years ago last night from Jordan. So Jordan like part of our conversation, and then he knew she no-showed yesterday. So he's like, Marianne,
She had a heart attack?
We were like, oh no,
Whoa.
stop, son.
Okay.
Just don't try.
Okay.
You had to remember, we're starting horrible rumors.
You didn't hear Marianne had a heart attack?
During Percy's biggest loser competition.
Oh yeah, you weren't there last night. We had something ridiculous and I like who was around. You missed all the joys.
I'm okay with that.
I'm okay with that, missing those joys.
Mm-hmm.
And we got the email to remind us to check domiciles when we meet at Humidity.
We had to check Airman last night that told us he wasn't accepting his extension.
And it was Denver to Colorado
Yeah,
Springs.
Yeah,
Which one?
As in,
Out of England.
out of England.
He's a treat.
Yeah, he pulled off and then he had his brand new FO pull off the TV.
Even though we wouldn't have done anything with the FO.
and then the poor flight attendant sat there and waited for our refill to come in, and they would have been in bed like an hour before the dumb pilots that just stayed on the
It was just a cause.
Then I gave him 10 hours, told him he was catching a cab in the morning. And
Yeah, he literally caused
I put him to bed, I made him take the refills. And I was like, yeah, go catch a cab in the morning. I'm completely out of parameters is that.
Who's working
Yeah, I
tonight?
just said, go.
Who all works tonight? Anybody?
I work tonight.
I work tonight. I know I normally don't ever work Saturdays, but I'm covering for Snyder. So I'll see you in there.
Hopefully Rob has an easier night tonight.
Yeah.
He had that night.
Okay, so I'm going to try and catch this up a little bit here. Just wanted to look, is everybody back in on this thing? Everybody can see this, right? Okay. Going back to this, just covering this real quick. So going back to the altimeter thing. So that one that we're going to go with, that one that says true altitude. Since existing conditions in a real atmosphere are seldom standard, altitude indications on the altimeter are seldom actual or true altitudes. True altitude is the actual vertical distance above mean sea level. If an altimeter does not indicate a true altitude, what does it indicate? So now we jump into indicated altitude, which shows the effect of mean temperature on the thickness of 3 columns of air. Pressures are equal at the bottoms and the tops of the 3 layers. Since an altimeter is essentially an aneroid barometer, altitude indicated by the altimeter at the top of each column would be the same. To see this effect more clearly, you see the picture below. In the warm air column, a pilot would fly at an altitude that is higher than the indicated altitude. In the cold air, the pilot would be lower. And then you have the standard one there in the middle. This is just going back to what we were talking about earlier. If it's warmer, it's going to show you're going to have to fly higher in order to have the indicated altitude match the true. And this is all based on your altimeter setting. So this is why you have to have it set correctly. Height indicated on the altimeter also changes with changes in surface pressure. A movable scale on the altimeter permits the pilot to adjust for surface pressure, but he or she has no means of adjusting the altimeter for mean temperature of the column of air below. Indicated altitude is the altitude above mean sea level indicated on the altimeter when set at the local altimeter setting. Since the altitude scale is adjustable, a pilot can set his or her altimeter to read true altitude at some specified height. Takeoff and landing are the most critical phases of flight. Therefore, airport elevation is the most desirable altitude for a true reading of the altimeter. The altimeter setting is the value to which the scale of the pressure altimeter is set so that the altimeter indicates the true altitude at field elevation. And this is basically what we were just talking about earlier. You get the altimeter setting from the METAR and you adjust that on your altimeter setting in the cockpit so that it reads the correct elevation of where you are currently at. To ensure the altimeter reading is compatible with altimeter readings of other aircraft in the vicinity, a pilot must ensure the altimeter setting is current. And this goes back to just, you want to make sure that everybody in the vicinity is at the altitude, reporting the same altitude. That's where you would have issues where, planes might, bump into each other. A pilot must ensure the altimeter setting is current. He or she must adjust it frequently while in flight, according to the nearest surface weather reporting station. That's just going back talking about like general aviation aircraft, kind of the example that I said, flying from here to Salt Lake. You would adjust your altimeter setting 5 or 6 times probably along your route as you're flying over different airports. This figure below shows the trouble a pilot can encounter if not vigilant in adjusting the altimeter during flight. As he or she flies from a high pressure to a low pressure, the plane is lower than the altimeter indicates. And that's just same thing what we were talking about earlier. If you don't adjust it in flight, your altitude's not going to report correctly. Temperature change effects on altimeter readings. This is just basically colder air, the altimeter reads too high. Standard, it should read correct. And then at warm, when it's warmer, it's going to read too low. So we already talked about the reasons why that would be bad. So corrected altitude. If a pilot could always determine mean temperature of a column of air between the aircraft and the surface, flight computers would be designed to use this mean temperature in computing true altitude. However, the only guide a pilot has to temperature below him is free air temperature at his altitude. Therefore, the flight computer uses outside air temperature to correct indicated altitude to the approximate true altitude. The corrected altitude is indicated altitude corrected for the temperature of the air column below the aircraft. The correction being based on the estimated deviation of the existing temperature from standard atmosphere temperature. That's the ISO deviation that I was talking about there. It is a close approximation to true altitude and is labeled true altitude on flight computers. It is close enough to the true altitude to be used for terrain clearance, provided that the pilot has his altimeter set to the value reported from a nearby reporting station. Pressure altitude. In the standard atmosphere, sea level pressure is 29.92 inches of mercury. Pressure decreases at a fixed rate upward through the standard atmosphere. Therefore, in the standard atmosphere, a given pressure exists at any specified altitude. Pressure altitude is the altitude above sea level shown by the altimeter when set to 29.92 inches. In other words, it is the altitude associated with a specified pressure measure by the static port when the altimeter is set to 29.92. This is also part of kind of what we were already discussing, that you set your altimeter to 29.92 to find out, what your actual pressure altitude is at an airport. As discussed earlier, constant pressure surfaces have different heights across them. Therefore, when flying at a specific pressure altitude, A pilot's true altitude will change with distance. However, since pressure altitudes are flown at or above flight level 180, that's 18,000 feet, a pilot will almost always be above the highest terrain features. So this is just going back, talking about how when you're at 18,000 feet or higher, you fly what this refers to as a constant pressure altitude. That's where when you pass through 18,000 feet, and you'll always see one of the pilots will adjust the altimeter setting from whatever it was at the airport they took off from to 29.92. So above 18,000, you always fly at a constant pressure altitude, that being 29.92. And that's so that everybody above 18,000 feet is reporting the same altitude regardless of where they're at. And that kind of was the same reason, because they're above the highest terrain features. Density altitude is the pressure altitude corrected for temperature deviations from the standard atmosphere. Density altitude bears the same relation to pressure altitude as true altitude does to indicated altitude. Density altitude is indirectly related to atmospheric density. This part we kind of talked about earlier, just that density, as the air density increases, the density altitude decreases. So airports with higher field elevations like Denver have lower pressure, lower density, and therefore higher density altitudes than airports with lower field elevations like New Orleans. Density altitude equals field elevation during standard atmospheric conditions, but conditions are rarely standard. Density altitude is higher or lower than standard at airports that report lower or higher than standard pressures. So this is just basically going kind of recovering kind of what we talked about already. Temperature is the most important factor since temperature has the greatest effect on density horizontally in the atmosphere. On a hot day, air becomes less dense, causing high density altitudes, and on cold days, air is denser, causing lower density altitudes. The dew point, which is the water vapor in the air, is also a contributing factor, but it's generally negligible. So this also is just talking about what we briefly covered. Density altitude is an index to aircraft performance. Skipping down there, so number one, it says it reduces power because the engines take in less air to support combustion. So this is just talking about how air density affects aircraft performance. So if you're at a higher density altitude, it becomes a hazard because, one, it reduces the power due to less air being taken in. It reduces thrust because there is less air for the propeller to work with, or a jet has less mass of gases to force out of the exhaust. And it reduces lift because the light air exerts less force on the airfoils. So this is just what we talked about earlier. When you're at a higher elevation and it's on a hotter day, the air density is less, therefore there's less lift on the wings, there's less, air in general. You think about less dense air, all that really is just there's not as much air. It's just the same principle as like when you hear about people climbing a mountain and they're going to really high altitudes. Well, they often need oxygen and supplemental things once they get to a really high altitude, and that's simply just because the air is so thin that there is not enough of it to support you. It's the same principle for an aircraft. It needs air, right? Just like a human needs air. So the higher you go and the hotter it is it's making the air thinner. So same principles. You don't have, an aircraft doesn't have what it needs to survive or perform in this case due to the air density. So a pilot cannot detect the effect of high density altitude on his airspeed indicator. The aircraft lifts off, climbs, cruises, glides, and lands at a prescribed indicated airspeed. But at a specified indicated airspeed, the pilot's true airspeed and ground speed increase proportionally as density altitude becomes higher. This was what I was talking about with the example of the headwind tailwind thing. when a pilot is taking off, he uses indicated airspeed. Okay, when you're looking at indicated airspeed, the indicated airspeed is simply just, if you just remember it this way, it's just simply what the aircraft thinks, how fast the aircraft thinks it's going. Okay, based on performance. Now, kind of like I said before, though, indicated airspeed rarely is ever anything even close to what actual airspeed is. So, like I was saying before, if a plane needs to take off, if it needs to take off at 140 knots, then that's based on indicated airspeed. So whatever it takes for the aircraft to think that it's going 140 is what, it's what it's going to have to do. And this is basically saying that a pilot, as he's rolling down the runway, he doesn't have, he's watching the indicated airspeed, because that's, when they're rolling down the runway, when it hits 140, that's when a pilot's going to call out, okay, rotate, and then the other pilot, the flying pilot, then pulls back on the yoke in order to begin takeoff process. But that's at a certain speed. They're called V speeds. But like I said before, those are all indicated airspeeds. And so, when there's a strong headwind, the aircraft thinks it's going 140, but because there's a 30 mile per hour headwind, it's really only going 110. So it's going slower than what it's showing in this case, but for takeoff that's good, because that means that it's going to take off faster, quicker, use less runway, and then climb out of there. And the opposite effect for a tailwind, it would end up having to go 170 for a 30 knot tailwind, which is going to make it use more runway. They're going to be going much slower than what it says, or sorry, much faster than what it really says, but nonetheless, the aircraft has to get to that indicated 140 speed. So does that all make sense with indicated versus true, kind of on how the relation is there? And like it's saying here, a pilot can't detect the effect of the air density on his airspeed indicator because he's looking, he can see it in other systems, but when he's rolling down a runway, he's not looking at like a thing that's measuring his tailwind or his headwind. He's looking at the V speeds right in front of him so that he knows when to say take off. So it becomes important, performance-wise. The net results are that high-density altitude lengthens a pilot's takeoff and landing rolls and reduces his or her rate of climb. Before liftoff, the plane must attain a faster ground speed and therefore needs more runway, and the reduced power and thrust add a need for still even more runway. The plane lands at a faster ground speed and therefore needs more room to stop. At a prescribed indicated airspeed, it is flying at a faster true airspeed, and therefore covers more distance in a given time, which means climbing at a shallower angle. Adding to this are the problems of reduced power and rate of climb. So this figure below shows the effects of density, altitude on takeoff distance and rate of climb. So you can kind of see here that at sea level, in a standard atmosphere, a plane is able to take off and climb at a higher degree than it can at 5,000 feet above sea level. It takes longer to go down the runway. Once it takes off, it can't climb as fast. You can see here that the takeoff roll between the two was a difference of 500 feet. When you look at high elevation airports, Salt Lake City, Denver, just are good examples. Salt Lake City's two primary runways are 12,000 feet long. In Denver, every single one of their runways is 12,000 feet long, and they have one runway that's 16,000 feet long. So you'll notice that at the major airports that are higher altitude airports like that, and obviously Denver is even 1,000 feet higher than Salt Lake is, so it's even more exaggerated in their case, but the reason their runways are so long is because in the summer they need that extra distance because aircraft performance is so degraded in the summer at a high elevation, high temperature, no air density environment that it literally takes an aircraft. They use up a ton of runway in order to get to the speed that they need to actually lift off. And once it lifts off, it's a really shallow climb, because even as it's climbing, that air density still has an effect on the aircraft. It can't, that same air density is not providing enough lift for the aircraft to climb at like a higher degree. You come to these shorter or these lower elevation areas, and St. George is not low elevation, but it's obviously half of what Denver is. So here we're 9,300 feet on the runway length. Still a pretty good long runway for here, but you go to like LA as an example. They have one runway that's like really long, that's like 11,000 feet, but all the other runways are like 9,000 feet or shorter, and that's because it's at sea level where it has really good performance. So they don't need long runways in LA. Like you take like an A380, like in the worst case, biggest plane you can think of, right? Performance-wise, it takes off no problem on a 9,000 foot runway in LA, simply because it's at sea level, the air density is high, they usually have a breeze. There's a lot of factors that contribute to all of this, but if you were to take that same airplane and throw it in Denver in the middle of summer, there's a pretty good chance that it may not even be able to take off at all. A lot of like the long-haul international flights in Denver, the reason they have the one runway that's 16,000 feet long is simply for all of like the really big planes. Like I think they have a couple of 747s that come in on British Airways. In the winter, it's no problem at all in Denver because it's so cold that the aircraft performance is not degraded at all, but it's only a summer problem. But in the middle of summer, a 747 taking off from Denver going to London, it has to use that 16,000 foot runway. Otherwise, it's not going to have enough runway to take off. So it really comes down to that. The reason why you never see 747s in Salt Lake City is because we don't have the runway long enough to support it, basically. You do see some occasionally, like in winter for cargo operations, but for like a scheduled passenger service, back when, if some of you guys remember, back when Salt Lake had the Tokyo flight, anybody remember that? Anybody around for that? We used to have Salt Lake to Narita on Delta. They dropped it in like 2009 or 10 due to the Depression. But anyway, one of the big reasons they dropped the flight though is because the aircraft performance leaving Salt Lake in the middle of summer was so degraded that they couldn't take, a lot of times they would have to bump off 30, 40, 50 people off of a plane that holds 250. They'd have to, they'd have to reduce the weight in order to maintain the performance, in order to take off on a 12,000 foot runway, basically. So just to kind of give you an idea, and even in the middle of summer now in Salt Lake, like the Paris flight, Amsterdam, London, those are timed now. At first, like a couple of years ago, they were really poorly timed. Like they were taken off at like 3 or 4 or 5 o'clock in the afternoon. And that's like the absolute worst time of the day, temperature-wise. If you think about it, that's the hottest time of the day, usually in summer. And so, like even the Paris flight that goes, you think of the factors overall of like a flight, but like a flight going from Salt Lake or Denver that goes east, like to Europe, is always going to have a tailwind, almost always, because jet streams go from west to east, generally speaking, and air flows west to east. So if you're flying east, you're almost always going to have a tailwind. If you're flying west, you're almost always going to have a headwind. That's why those of you that have gone to like Hawaii, it always takes longer to fly to Hawaii than it does to fly back from Hawaii, and it's usually an hour difference. But Salt Lake and Denver, because they're high elevation, the flights going to Europe normally are better because they're not going to use as much fuel, because normally those flights have tailwinds going all the way to Europe, so they don't need as much fuel and everything else. But when they leave Europe to come back to Denver, and Salt Lake. Those flights, so like in Paris, Amsterdam, London, those areas, or some of the German flights, in Denver, those are all leaving, like most of those European areas are airports that are at sea level that have really good performance, like Paris, London, those are pretty much sea level airports. So if those ones are leaving, coming back into the wind, but because they're leaving from an airport that has good performance, they can get all the people and fuel on it. Whereas, like you take the example of Salt Lake to Tokyo now is going the opposite way. It's leaving from a high elevation airport, going into the headwind, going all the way across the Pacific, headwind the entire time, all the way to Narita, and it just became the economical factors of the flight just became so bad that that's a big part of the reason that they got rid of it, because they didn't have the performance. Even in Denver, even on their 16,000-foot runway, some of their flights, like going to, even their 747s that go to London and things like that, the British Airways, the Lufthansa flights, in the middle of summer, a lot of those, they have to time them differently so that they take off like at night, like at 10 p.m. when it's dark and cool, in order to even, be able to get the performance. Because if it took off in that afternoon time, they don't get the performance at all. So I'm kind of just throwing, I guess, in, helpful non-rev terms, I guess. It basically wasn't, so Denver never even had an Asia flight until the 787 came out. The 787 is such like a good performing airplane, and it's like built for high elevation, high temperature situations. So when the 787 came out, it's like a custom built plane in a lot of cases, perfect for like a Denver environment to actually fly into the headwind, going clear across the Pacific over to Tokyo. But it's such a good performing airplane that it doesn't take much weight penalty hits or performance degradations, even in the middle of summer leaving Denver. And it leaves earlier in the day, but that's a big part of like long haul flights is like they, if they don't make sense, like they have to time them right out of these airports. Otherwise, just a couple of hours difference will make a big difference on how many people they can take. So, let's see. High density altitude can also be a problem at cruising altitude. When air temperature is higher than standard, the higher density altitude lowers the overall capability for the plane to fly higher, or the service ceiling. So, for example, if a temperature at a pressure altitude of 10,000 feet is 20 degrees Celsius, the density altitude is 12,700 feet. So a pilot's aircraft will perform as if it were at 12,700 feet with a normal temperature of -8 degrees Celsius. So that's basically saying, and it's even the same, like if it's really hot outside, and we have measurements of the wind and the temperature and everything at every altitude when we do flight planning. So like the CRJ 700, just as an example, has a service ceiling of 41,000 feet. That basically means that under the best conditions, the highest it could ever fly is 41,000 feet. However, if the air is really hot, even at 38,000 feet, so at 38,000, 39,000, 40,000 feet, you still have temperatures, and we still get temperatures reported. And those temperatures are always negative, but everybody can imagine it's really cold at those temperatures, but there's still an ISA temperature for 39,000 feet. So every altitude has an ISA temperature of what it should be. So if you were to take that same formula, 15 degrees Celsius at sea level, and do the math all the way up to 38,000 feet, you minus the 2 degrees all the way up. Well, I'm just trying to do some quick math, but ISA at 39,000 feet should be roughly somewhere like -63, -60 something, basically. I think -63. So the easiest way to do it is take the altitude times it by 2, and then minus 15. So what's 39 times 2 minus 15? 63? Okay, so 63. So the air temperature at 39,000 feet, if it's at ISA, should be negative 63 degrees. And then you always convert it to negative if it's over 24,000 feet. We'll get into that later, but it should be negative 63. So then we take our little chart and we see, okay, well, what is the temperature at 39,000 feet? Well, today it's minus 55. It should be minus 63. When you're obviously in the negatives, if it's a lower temperature, technically it's warmer. So in that case, you would be ISA plus 8. If it's so. Anyway, then you got to use that chart. So if you're using an ISA, you'd have to go up to an ISA plus 10 chart in that case. But you would have to go, if you're using ISA plus 10 as your deviation, then that's going to take your overall capability to fly higher. It's going to reduce. Because if the service ceiling is based on a standard temperature, 41,000 feet would be the top. If you're warmer than that, then you're going to see, and you'll see this later on the charts, but you'll see that if it's a really hot day, your max altitude is going to be reduced. Like maybe today, because it's so warm, your max altitude is only going to be 36,000 feet because of the weight of the aircraft, the temperature at that altitude, and other factors. But this is saying is that the service ceiling of an aircraft is lowered if the density altitude is higher or lower, basically. Okay. So is everybody good on everything altimeter-wise? Any questions on altimeter stuff? Pressure, altitude, density, the temperature, how they affect it? Obviously, this is all available to go back. If you need to go back and look at specific things, you can go back. The big things that you just want to take from that altimeter pressure stuff is just that the higher pressure, or sorry, the higher temperature, the higher elevation, that less dense air will degrade aircraft performance. That's all you're really caring about as a dispatcher in the end with all of this stuff. It's just what effect does this have on the flight that I'm planning? And that's just simply lower pressure, higher temperatures, higher elevations. You just got to know as a dispatcher that that formula of stuff, any one of those things individually and obviously collectively is going to decrease the performance of the flight that you're planning. So, like when we're asking dispatchers, well, how many people can this flight take? Or if this flight's bumping people out, wherever it's leaving from, a lot of that is based on just simply the weather dynamics of whatever airport it's leaving from. So, like I said, you don't need to get too involved in, this is millibars and this is the science behind it. None of that. You don't use any of that. It's just simply, you just got to understand the dynamics of it is of why it's doing it, really. I mean, technically when you end up dispatching and you're doing everything on a computer, it's just telling you the number. It's not like you're figuring it out, but you still got to understand why, that's just the big thing. It's just understanding why it's changing, because a lot of times you got to be able to answer those questions. You're going to get the pilot calling you up and saying, well, why am I weight restricted? If you don't know why right off the top of your head, then that's a problem, So you got to know, you got to be able to tell them, oh, well, the reason is because Denver's so freaking hot today, and we're taking hits because Denver's hot, pressure, altitude is clear up, So and they understand that stuff. They just, they're not necessarily, sometimes they're calling you as they're driving in, hey, I just got the release on my phone and I saw that, whatever, or I want to take more fuel. Why can't I take more fuel? Well, it's because we're up against max takeoff weight. And a lot of that is because of the performance, So just those things, they all play in effect. And like I say, we'll be going over this stuff all later more. Now we're going to talk about wind. Let's see. Wind is, everybody knows what wind is. Wind is the air in motion relative to the surface of the earth. Although we can't actually see air moving, we can measure its motion by force that it applies on objects. For example, leaves rustling or trees swaying on a windy day indicate that the wind is blowing, in case we didn't know. Winds are a major factor to both weather and aircraft. Winds cause the formation, dissipation, and redistribution of weather. Winds also affect aircraft during all phases of flight. This chapter discusses how winds are named and the origin of the wind. Naming of the wind. Wind is named according to the direction from which it is blowing. For example, a west wind indicates the wind is blowing from the west to the east. In aviation, 36 points of the compass are normally used to represent the direction from which the wind is blowing. For example, north winds come from 360 degrees, east from 90, south from 180, and west from 270. So just so everybody knows kind of what this is meaning and let's go back to our, I think we're looking at, LA is not a good one to look at. Let's go back to our St. George. That's not a good one either. Trying to find somewhere that has some wind. Let's see if San Fran has wind. Okay, there we go. So when you're looking at a METAR here, this right here, if it's big enough for you guys to read, it basically says 33013 KT. Does everybody see that? So what that means is that so it's so the wind is coming from 330. What's that?
Northeast.
Yeah. So the first part, the first three there is basically telling you what direction it's coming from. So this goes in increments of 10. So if you see 33, that means 330. You're never going to see anything other than to the nearest 10. You're never going to see 332, for an example. It's always going to be 300, 310, 320, 330, 340. So you'll never see anything in between to the nearest 10, if that makes sense. Okay. The next one, so the next one's a 0, but that's actually the next, so the first two are the actual wind direction. Okay. The next 3 are the wind speed. So in this case, it's 13 knots. So here in St. George, or sorry, this is San Fran. So in San Fran, the wind is coming from 330 at 13 knots. So it's kind of, you get used to it as a dispatcher, obviously, but just so you kind of know.
Did you say the first 2?
The first 2 is the wind direction that it's coming from. So if I have to have a compass here, so this right here is 360, okay? So it's not 0, it's 360. 360 is directly north. Then obviously 180. And so this over here is going to be, let's see, so if we're going this way, so it's going to be 90 and maybe 270. And the 2's kind of good. Anyway, so the San Fran wind, it says that it's coming from 330. That means that the wind is not that it's blowing towards 330, that means that it's coming from 330. So the wind is coming
this direction. It's technically, if you were to say which way is the wind blowing, it's really blowing, you know, the exact inverse of this. So it's really blowing at like 110, you know, or whatever, 120, 110, somewhere in there. That's the direction it's actually traveling. So the reason why this is kind of important to show is that this is the only thing in aviation that's backwards when you're talking about directions, okay? It's everything else you do, like when you're in an aircraft, I'm flying, you know, if I was in an aircraft flying, you know, 330, I'm heading that direction. You know, so it's all, people sometimes get confused on this when they first learn it, but it'll just become secondhand thing later on. But if you're flying 330 and then you see a wind report of 330, that means you have a direct headwind. A lot of people at first think that it's flying with the wind instead of against the wind. So the wind really, in this case, is going like 110, 120 degrees, you know. And if you were flying 120, in this case, you'd have like a direct tailwind. So just remember that the wind is always, you got to flip-flop it, it's always
Basically just headwind, wind is headwind.
Yeah,
Think of it that way.
exactly, yeah. Or just that that's where it's coming from. So here in St. George, the runway is 19 and 1. If the wind here was reporting, you know, 190 at 15, that means, you know, the wind is coming from 190 degrees at 15 knots. It would mean that you would land on 19. So that would be your headwind. So because when you land, the runway numbering is based on the heading of the aircraft. So if you're landing on runway 19, that means that as you are approaching the airport, you're actually on a heading of 190. That's what you're flying. So you're heading 190 degrees, and therefore the runway alignment is that's why they call it runway 19, is because it's aligned with 190 degrees. So if you get a wind reporting of 190 at 15, that's what you want, because that means that you're landing into the wind, and you would want to use 19. So like I say, a lot of this stuff too, when we do flight planning especially, we'll be looking at every flight, and you'll get very used to knowing how to look at this and how to determine what runway you're going to use to land on and everything else. But just wanted to get that kind of out of the way there.
I'm so sorry. I still don't understand why on those numbers, the first two, you just always tack on a 0.
So no. So for instance, if it was really windy, the next 3 are technically for the speed. The only reason it's a 0 is because the speed of the wind was less than 100. So now if you were to have a really windy day, you know, extremely hurricane type windy day, you know, you could see 330 at, you know, 330 then 110, and that would just mean that the wind is coming from 330 at 110 knots.
Oh,
that's all it is.
Okay, I got you. So it's not. Okay, that makes sense.
Yeah. But normally, you know, from a METAR perspective, you're normally not going to see that. You'll only see that type of a wind speed up at the high altitudes when you're doing flight planning for your cruise altitude stuff. So yeah, so the first 2 are just the direction it's coming from, and then the next 3 are for the speed. Forces that affect the wind. 3 primary forces affect the flow of wind: pressure, gradient force, Coriolis force, and friction. So pressure gradient force is driven by pressure differences which create a force called pressure gradient force. A lot of this stuff is just the science of wind. Don't got to worry too much about it. So whenever pressure differences develop over an area, the pressure gradient force makes the wind blow in an attempt to equalize the pressure differences. This force is identified by height contour gradients on constant pressure charts and isobar gradients on surface charts. So basically what all this is saying
is that, and the whole reason that you get wind in the first place is you have a high pressure and a low pressure. What always happens with pressure systems is low pressures are always, if they're both highs and lows can move in onto each other, right? So they can overtake each other basically. But what happens if a low pressure system is taking over or coming in onto a high pressure system? It'll always come in underneath it, okay? Because you just got to remember, low pressure stays to the ground, and when it overtakes a high pressure, it actually comes in underneath it and then pushes it out, if that makes sense. If you remember, low pressures, they always are the cyclonic, so they're counterclockwise rotation. So when you have a low pressure coming in, what always happens in the wind environment or the pressure center environment is that pressure centers, like highs and lows, are always attempting to take each other over. And this is what creates wind. A low pressure wants to always, come in. I mean, generally speaking, your weather moves from west to east. So if you have, let's see if I can go back to my chart here, just to kind of show this a little bit better. So these pressure centers, like you have a high over here, a high here, a low here, these are always basically trying to overtake each other. So, but they're still moving from the west to the east. So they'll still move against each other, but as like a high is coming in here, like you can see this high that's over Nevada right here. So if you think about a high, it has an anticyclonic rotation. So it's rotating like this, if you can see the mouse moving. It's rotating clockwise. So what will happen as this high gravitates over Utah, what will happen is you'll see the wind from a high is constantly trying to go anticyclonic. So basically what happens is if you have a high over here, its wind is going this way. And then you have, let's say you've got a low sitting over here. Its wind is going that way. So, but basically what will happen though, so these are spinning. This one's spinning this way, and this one is spinning this way. As these, generally overall, here in the U.S., they're still moving, from west to east. So even though they're spinning, they're still moving this direction. So what will happen, if we're here, if we're right here in St. George, let's say, and this low is right to the north, if we're located right here on this particular edge of the low pressure system, you'll see wind coming from, if this is north, you see the wind basically coming out of that direction. You'll see it, coming this way. As this moves across, like once it's over here, then, if we, I'll just move the dot to kind of represent, if the low pressure system was, let's say, to the south of us, but still moving, then you would see, you're going to see the wind basically from wherever you're located based on the pressure center. So sometimes you get it from this direction. It all just depends on where the low pressure system is coming from. Now, as this moves through, it's constantly moving this direction still. So, like in a couple of hours, you might be right here, and then it's coming from that direction instead of straight from the east. That's where the wind changes. But as this one then moves in, you can see that the wind was coming this way. Well, this one, is now moving like this, and this one was moving like this. That's kind of how they move into each other. You start getting, you can tell when a low pressure system has passed out and a high pressure is moving in, because as the low pressure leaves, the wind will shift from coming, from the east to where it gravitates towards the north. As the wind shifts
blowing from the north, you can tell that it's a low pressure. It's basically, this is called frontal passage is what the term is called, but there's several other ways you can tell other than just wind, but this, you can tell that a low pressure is leaving and a high pressure, the wind will still be coming from the same direction, but as the wind comes from the northeast, shifts to the north, basically when it's dead north, you'll know that you're basically right in between a front. That's typically how you can kind of decipher without actually looking at a weather map. And then the wind obviously begins to shift this way. And now if you know that you have a northwest wind, typically that's the front edge of a high pressure system coming in. So, if you're down here, it's kind of the same deal. It's still, even if it's from the northwest, it's still kind of, the edge, even though it's this edge rather than this edge, or, it'll vary a little bit based on where you're located, but, you can kind of see, you can kind of base the wind a little bit off of that.
So last night, 10 o'clock, just as the example with that flight coming in, that American flight coming in last night, we were like right at the top where you have that top dot in order for it to have such a good landing, because it would be coming from the north, and now if we look outside, the wind's blowing again, so that high is coming back around, having it go back towards the wind, towards the south, or towards the north.
Yeah, I mean, and the other thing too is that the wind, there's the other thing with airports in general is that when you're on the ground, there are obviously other things that'll affect the wind direction. Like the topography of the area obviously affects it a lot, and that's what actually has the largest effect. When you're up in the air above the mountains, that's when you get that effect the most, because there's nothing blocking the wind. Okay, so that's when you get the true wind direction with frontal passage. Now when you're down here on the ground, obviously the wind is hitting into the mountains and it's making it shift this way. That's what creates wind shear. That's what creates local wind, deviation basically, is what it's doing. So like for instance, if you look at the alignment of the St. George runway, primarily you usually, 9 times out of 10, you land on 19. It's pretty rare to land on 1, and you can probably attest to that. But 9 times out of 10, you're going to land on 19. And that's because, generally speaking, the wind here in St. George is normally coming from the northwest, or the northeast, I should say. But the reason for that is because if you zoom out on St. George and you look at the overall topography of this area, you'll notice that it aligns itself with the canyon. And the reason why it aligns itself with the canyon, the canyon going up to Cedar, is because what happens when that wind is coming around like that, it hits into the mountains, but when it hits into a canyon like that, the canyon acts as a huge funnel for the wind, and it just blows, either up the canyon or down the canyon, depending on,
Well, and it's almost aligned directly with the gorge.
Yeah, exactly. So you look at those two things, and then that's kind of how you can gather a little bit more information about the local wind environment. And we're going to talk about local winds here in a minute, but if you had no topography at all, if everything was just perfectly flat, then that's how your wind systems would always be. Nothing affecting it. When you get out onto the plains and you get out, Midwest and things like that, generally, I mean, that's how your wind works. And if you notice out there, storm systems are way more dramatic. They're capable of growing a lot bigger. Thunderstorms and things like that are way worse out in the the Midwest going towards the east. And that's simply because there's no terrain to deflect all that stuff. It's able just to sit out there, and it also allows storm systems to build because they don't have anything keeping it from gathering, basically nothing interrupting its airflow is basically the reason why they are able to grow out there so big. Now here obviously you do get thunderstorms, but out here they're all considered pop-up thunderstorms. It's like it's all based on I'm kind of getting a little off topic, but thunderstorms here are just sporadic, and it's just a cell that pops up, moves over, it lasts about 10, 15 minutes, maybe 20 minutes, moves over, and then dies out. You see, like for instance today as an example, on this, you can see a huge line of thunderstorms, but you always see this. In the summer, the springtime, when you look out in the Midwest, you see this huge line that extends from Texas clear up to Chicago, like in today's case, of thunderstorms. You never see that in the West because there's mountains. There's not enough, there's not enough, it can't ever gather enough energy in a mountainous climate to actually form like this. You have to have flat environment to where it can all just align itself, and then it just moves across and dies out. So, but you don't ever see that out here because it's impossible to form like that out here. So,
what causes the microburst here?
Microburst is just simply when a thunderstorm is dying out. So if you get a thunderstorm cell that pops up over St. George, and basically when a thunderstorm gets into what's called the dissipation stage, that's basically where the airflow, so when a thunderstorm dies out, all of the air that it was using, it's basically dropping. So when it's in the dissipation stage, all of the air suddenly kind of falls out. So you'll never normally see a microburst when the thunderstorm is mature, and when you have the lightning, the thunder, that's like the mature stage. But when it starts to fizzle out and then it dies out, that wind and everything that it is concealing, suddenly drops out. It's almost like a funnel, like you think about it like, like a lab service on an airplane. You're just pulling the thing, and then all of a sudden it's just pulling the cord and dropping out all of the energy from the storm, and all the air just falls to the ground. And if you think about it like taking a drink and just pouring it, that's literally the exact same effect. It hits the ground and then it just splashes outward. So a microburst, that's all it is. It's a dissipating thunderstorm that's basically losing its energy, and the air is falling out of it. The air falls straight down, hits the ground, and as it hits the ground, it just hits it, and then it goes outward like this. And that's sometimes, depending on the size of the thunderstorm cell, though, that the severity of a microburst and the severity of the wind shear that it causes is just directly associated with how strong the thunderstorm was. So if it was a really strong thunderstorm, that when it gets rid of the wind like that, it can obviously become extremely powerful, like hurricane tornadic type force. So, but yeah, that's basically what causes it, though. So it just has to happen in the right place. The reason you always see them in Denver is because if you notice how Denver's located, it's obviously close to the mountains, but it's really the beginning of the plains. So Denver doesn't have, it only has the protection on the west side. So you'll never see a thunderstorm move in from the west in Denver. It never comes over the mountains and then drops in. It always is from the south, from the north, or whatever. But the reason why it's able to build in that area is because there's nothing stopping it. Like Salt Lake has the protection on every side of the mountains, And although you do see the pop-up storms, you don't see the severity like you do in Denver, because Denver is totally exposed on really three sides. So let's see. Pressure gradient force. So basically, going back to the pressure systems, they move in on top of each other, and that's how you can see. You can tell when you've had frontal passage because you'll get a shift in the wind, or you can tell that you're getting a frontal passage coming through because if the wind shifts. Now, there's other differences between highs and lows. Like a low temperature or a low pressure system, will bring with it a temperature change, a pressure change. So obviously low pressure, high pressure, you can imagine there's all sorts of differences. The wind is just one element of those. But as the frontal passage comes through and you're being overtaken from a high to a low or a low to a high, you can normally tell what that is because the pressure, the temperature will either drop or it'll increase, the actual altimeter, the barometer setting, the pressure in inches of mercury will increase, decrease as well, and then the wind will shift. So, and everybody has seen that here, I'm sure. Like you've got a nice sunny day like this, 20 minutes from now, all of a sudden the wind shifts, it becomes cool. Like yesterday, there was that low pressure that moved through. You're talking about, just showed on the map. Yesterday was a very cool day, and it had the breeze. And that was simply, those are all associations with a low pressure system that came in, moved out. Now it's moved out, and now you're back to the high pressure system, moving in, essentially. Wind speed is directly proportional. Let's see, let's jump down to Coriolis effect. Coriolis effect is just simply the Earth's rotation that causes the wind. So you have stuff like mountains and things like that that are on Earth, and the Earth is spinning. And because the Earth is spinning and has all of this topography, and it's not perfectly flat, those, if you think about a mountain, you think about, something spinning, obviously those things are creating what are called a Coriolis effect. They're trapping the air, or they're causing the air to spin in different directions. I'll read this. This is just going to be brief, but Coriolis force, a moving mass travels in a straight line until acted on by some outside force. However, if one views the moving mass from a rotating platform, the path of the moving mass relative to his platform appears to be deflected or curved. To illustrate, consider a turntable. If one uses a pencil or a ruler to draw a straight line from the center to the outer edge of the turntable, the pencil will have traveled in a straight line. However, stopping the turntable, it is evident that the line spirals outward from the center. So, kind of a weird example, but I guess it's a good example, but kind of there's the better examples is just thinking about the Earth and having mountains, and it's basically pushing and causing air to spin. The similar apparent force deflects moving particles on Earth. Because the Earth is spherical, the deflective force is much more complex than the simple turntable example. Although the force is termed apparent to us on Earth, it is very real. The principle was first explained by blah, 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 and now carries his name, the Coriolis force. Coriolis force affects all moving objects. The force deflects air to the right in the northern hemisphere and to the left in the southern hemisphere. Coriolis force is at a right angle to wind direction and directly proportional to wind speed. That is, as wind speed increases, Coriolis force increases. Let's see, Coriolis force. I mean, long story short, Coriolis force really, the only time we ever talk about it is when we're talking about weather in class. So you'll probably never really talk about it out on the dispatch floor. But just understanding what it is, it's just the Earth is spinning and it's causing wind to deflect, and also the topography of the Earth also causes wind to be deflected. In the north, it deflects to the right. In the south, the southern hemisphere, it deflects to the left. I mean, if you came away knowing no more than just that, then you'd be fine. So that's pretty much Coriolis force magnitude variations with speed. Greater the speed, greater the friction. Friction force magnitude variations with terrain roughness. So this is just going back, like in a higher terrain environment where you have mountains and stuff, the friction is going to be more pronounced. We already kind of covered that. So, yeah. Upper air wind, let's jump to that. Upper air wind in the atmosphere above the friction layer. Let's see, the lowest few thousand feet. Okay, so This is basically just saying in the atmosphere above, so the friction layer is just basically the level that that the Coriolis friction effect basically takes place, but only the pressure gradient force and the Coriolis force affect the horizontal movement of air or motion of air. Remember that the pressure gradient force drives the wind and is oriented perpendicular to height contours. When pressure gradient force is first established, wind begins to blow from higher to lower heights directly across the contours. However, the instant air begins moving, Coriolis force deflects it to the right. Soon the wind is deflected a full 90 degrees and is parallel to the contours. At this time, Coriolis force exactly balances pressure gradient force, as shown in figure 7-8. With the forces in balance, the wind will remain parallel to contours. This is called geostrophic wind. Yeah, not too much we got to really consider here. So let's surface wind. At the surface of the Earth, all three forces come into play. As frictional force slows the wind speed, Coriolis force decreases. However, friction does not affect pressure gradient force. Pressure gradient force and Coriolis force are no longer in balance. The stronger pressure gradient force turns the wind at an angle across the isobars toward lower pressure until the three forces balance. So this is basically just saying, so at higher altitudes, the wind speed is higher because there's nothing affecting it. Going back to what we were talking about, like when you go up to 38,000 feet, and in the 30,000 foot to 40,000 foot level, the wind is normally always 100 knots or more in in whatever direction that it's traveling. At the lower you go in altitude, the less the wind is. So and coming all the way down to the surface, once you obviously it's not normal ever for us to have 100-mile-per-hour wind here. So it takes a major act of nature, but it's basically just saying that at elevation on the ground, everything that affects the wind, such as the terrain, the Coriolis effect, and everything else, slows the wind down and makes it take on basically what's called like a local element based on where you live, based on the mountains, based on everything else. That's what determines the local wind, and also the temperature of the ground, the temperature of the air. There's a lot of things that we'll look into it here in a minute when we get to the local portion, but that's all you kind of need to understand here, is that surface wind is basically being affected by several other things than just what you see in the upper atmosphere. When you're looking upper air, you're talking about the highs and the lows and just the movement that they have mixed with the Coriolis effect. And then when you're talking about surface, you've got to take into account terrain, pressure gradient force changes, and the Coriolis effect still obviously affects it as well, and just the fact that it's lower. So the angle of surface wind to isobars is about 10 degrees over water. That's not anything we care about too much, increasing to as high as 45. In the northern hemisphere, surface wind spirals clockwise and outward from high pressures and counterclockwise and inward from low pressures. In mountainous regions, one often has difficulty relating surface wind to pressure gradient because of the immense friction and also because of local terrain effects on pressure. That's kind of what I was just talking about. Oh, I forgot to get rid of all this part. Okay. So jet streams. Now we're jumping into the jet streams down here. Jet streams are relatively narrow bands of strong wind in the upper levels of the atmosphere. The winds blow from west to east in jet streams, but the flow often meanders southward and northward in waves. Jet streams follow the boundaries between hot and cold air. Since these hot and cold air boundaries are most pronounced in winter, the jet streams are the strongest for both the northern and southern hemisphere winters. Just as a relation to this that you guys see, in the winter, like you take some of those long haul flights that we do, like the Alaska flights, the Seattle, Milwaukee's, the Portland, St. Louis, the ones that have block issues. It's way more exaggerated in the winter because of the jet stream and the headwinds that they have to deal with. So, when we have to end up doing like if you have a Portland, St. Louis flight, it makes it out there no problem, but then it goes St. Louis, Portland, and then we realize that it can't make it back because of how strong the headwinds are. Well, it's just talking about in the winter, the jet stream is so much more increased in speed, and that's just because of kind of what it's saying here, that the highs and low pressure systems have so much higher degree of varying temperatures that it causes the jet stream to basically be able to gather a lot more speed, because all the jet stream is doing is it's following the contour of these lines. So just if I could kind of give you an idea, I could show it on a chart, but if you got a high here, a low here, a high here, another low here, I mean, just scattered throughout the U.S. The jet stream, what it's going to do is it's going to follow these patterns. So it's going to be coming up, let's say it's coming up this way. It's going to hit this high, and then it's going to deflect down like this, and then it's going to go straight, and it's going to hit this low, and then it's going to deflect like this. You kind of see this is why the jet stream goes like this. It's because it's just following the contours of these. And so then it would hit into this high, and then it would be deflected. And if this low was down here, then it would come travel clear down here, and then, same thing. That's why it goes straight. If you don't have a lot of systems out there, or if you have like a bunch of high pressure systems, like let's say this one was a high instead of a low, and it's actually spinning this way, well then this would come right over the top, and it would just go straight, because it would pick it up right here, and it would just carry it over. So when you see the jet stream just going straight, it's because it's picking up, it's going over pressure systems that are the same, they're all highs, or they're all lows, or whatever. It's just following, it's not going to meander because it's not having to change temperature, basically. And temperature is what really affects it. So that's kind of what will cause the changes. But if it's just going in a straight line across the U.S., that generally means that across the U.S. is probably similar weather. That's all that it really means. So if we can look at the jet stream real quick here. Like today's jet stream. Where are you? There's the 300 millibar one. This is showing it with isobars, but you can see the jet stream. If you were to follow it, it's basically going like this and then dipping down. So if you can kind of see, if you remember how there was that high sitting over Nevada, there's that low that's like down here, and then there's that high that's over here. And you can kind of see that's exactly what it's doing. It's coming in, it's coming over the top of that high, it's being deflected down underneath the low, and then back up over the high, and then going out this way. If you remember, there was that huge front right here. It basically just comes back up underneath that low, and it's staying on the left side. It normally stays on the polar side of fronts. So if you remember, there's that huge storm system that goes from Texas to Chicago. You can kind of see it. So the jet stream will always usually stay on the polar side of like a cold front. So we'll talk about that later, but I wish this kind of had a better like blue line, but you kind of see it just comes in, it dips down straight over. This is also, you can tell why it's affecting the like the wind here, like why we have really strong north winds. Like last night, if you go straight up above us right now, the upper air over Utah right now is really strong from north to south, because the jet stream is literally right over the top of us right now. So, but it's blowing from north to south, and then as you go down over Arizona, down dip into Mexico, you'll see the shift where the jet stream now turns, curves back up, and now if you're flying over the Midwest, the jet stream is going north to south, or sorry, south blowing to the north. So just to kind of give you an idea. Why does the jet stream winds blow from west to east? As stated in the previous section, if the Earth was not rotating, the warm air would rise at the equator and move toward both the poles. The Earth's rotation divides the circulation into 3 cells. Likewise, the Earth's rotation is responsible for the jet stream. The motion of the air is not directly north and south, but rather is affected by the momentum that the air has as it moves away from the equator and how fast a location on or above the Earth moves relative to the Earth's axis. An object's speed relative to the Earth's axis depends on its location. Someone standing on the equator is moving much faster than someone standing on the 45-degree latitude line. In figure 8.3, the person at the position on the equator arrives at the yellow line sooner than the other two. Someone standing on a pole is not moving at all. So that's kind of, you can imagine in your head. The momentum of air as it travels around the Earth is conserved, which means as the air that is over the equator starts moving toward one of the poles, it keeps its eastward motion constant. The Earth below the air, however, moves slower as that air travels toward the poles. The result is that the air moves faster and faster in an easterly direction relative to the Earth's surface below. The farther it moves from the equator, the farther it moves away from the equator. So yeah, so I mean, that's ultimately why wind goes west to east here. It's just simply because that's the rotation of the Earth. So it's deflecting that direction. So this is talking about the location. In addition, with the 3-cell circulations mentioned previously, the regions around 30 degrees north. Let me see if this one even about it. All this is basically talking about here is just the jet stream, moving between the cells and the pressure systems, but this really isn't anything too much. So there's different types of jet streams. There's polar jet streams, subtropical jet streams, both the northern hemisphere, southern hemisphere. So a lot of times when you're looking at the weather, you'll see several different jet streams going across the United States. And you'll see one that comes from up in Canada that dips down and goes over, one that comes up from like from the southwest, coming up from the equator. So you'll and then even several other, there can be multiple coming from both directions. Sometimes you see like 3 or 4 or 5 of them that are just crossing the U.S. just at any given time. We kind of already talked about. Jet streams also follow the sun in that as the sun's elevation increases each day, in the spring the jet streams shift north, moving into Canada. By summer, as autumn approaches, the sun's elevation decreases. It's kind of going back to the same thing in the winter. That's why the jet streams are a lot stronger. They're when we're in the warmer months, they actually move more northerly, and so they always like to stay kind of where the air is cooler. So in the winter, obviously, as the sun moves down to the equator and down in to the southern hemisphere more, then that allows that jet stream, those polar jet streams up in Canada and over the Arctic, to now move and centralize over the United States. But kind of the same principle we were talking about earlier. Then in the summer, it pushes them back up higher. The jet stream is often indicated by a line on maps and shown by television meteorologists. The line generally points to the location of the strongest wind. In reality, jet streams are typically much wider. They are less a distinct location and more a region where winds increase toward a core of the highest speed. One way of visualizing this is to consider a river. A river's current is generally the strongest in the center, with decreasing strength as one approaches the river's bank. It can be said that jet streams are rivers of air. Okay, now we're going to jump into local winds. Local winds are small-scale wind fields driven by, let's see, diurnal heating? I don't know how to pronounce that word. Or cooling of the ground. Air temperature differences develop over adjacent surfaces. Air in contact with the ground heats during the day and cools at night. Low-level pressure gradients develop with higher pressure over the cooler, denser air and lower pressure over the warmer, less dense air. So this is just basically diving into, like, you know, different local areas depending on where you live. You know, the air can change during the day, but it's not really necessarily have anything to do with like a high or a low pressure moving in. It just has more to do with like the local conditions of where you live and like what's going on. Like a perfect example of this would be like if you ever notice, like when you're on the coast, if you're in California or if you're in Hawaii or wherever, if you're out, let's say you're on the beach, you know, during the day, you normally will have a sea breeze. I mean, I'm sure everybody's kind of seen like a sea breeze type environment. You'll have it all day during the day, and basically the reason like why a sea breeze exists is because if you compare water, if you're right next to a large body of water or an ocean, as the sun comes up and as it heats up things, the land heats up a lot faster than water heats up. So water obviously takes a lot longer to absorb heat and to actually get warm. So, I mean, I'm sure everybody in here has, you know, jumped into the ocean, jumped into a lake or whatever, and it's always feels cool, you know. I mean, sometimes it's warm, but it's never going to be as warm as the outside air, essentially, usually, or sometimes it is warmer, but it just depends on the temperature, you know, differences. But a sea breeze basically is caused because, like, as the sun comes up, the land warms up, and the ocean is still at a cooler temperature than the land. So what happens is that the air over the ocean wants to escape towards the, you know, air is always kind of like when you look at the high and the low pressures, it's developing kind of a temperature gradient difference, and lower temperature air and higher temperature air, they always want to try to converge, or like, you know, they will always want to overtake each other. But basically air usually is always trying to escape from the lower temperature to the higher temperature. So when you have the cool ocean and the air right above it, it causes that air to move over, you know, to come in towards the land, and that's why you get a sea breeze basically, because the warm surface, and I guess you can kind of see it actually on this. If you were to imagine that the cool surface on this was the water and the warm surface was land, then you kind of see that this pattern develops where the air blows in when it's on the ground. The air wants to move over to the warm, so you get the air on the ground blowing off of the cold surface towards the warm surface, and then once it hits the warm surface, it starts to warm up again, and then it causes it to lift, because as air warms up, it creates a lifting action basically. So it basically creates like a kind of a small high-low pressure, if that makes sense. But it's not like a real one like we see on a weather map, but it's like a little tiny local one, like a, you know, a little just that only exists just right where you're at basically. So you can kind of see it will rotate up, and then that same air will then, as it gets warm and higher up, it wants to move back, you know, counterclockwise back over towards the cool, and then it goes back out over the ocean, it cools down, it falls down again. It just the same motion creates. Now when you get nighttime and the sun goes down in this same exact environment at night, where you have a sea breeze during the day, once the sun goes down, that same location will almost always have a land breeze at night. So if you're sitting out on the beach at night, the wind almost always is blowing from the land to the sea for the exact opposite reasons, because the ocean heated up during the day, and now it's just transversed. The ocean is now warmer than the land because the land cools and heats up so much faster. When the sun goes down, the land ends up cooling much faster than the ocean, and then it drops below, and so you just get the exact reverse effect, that the wind now goes the other direction and blows out to sea at night, and then changes back up in the morning once it starts warming up. I think this thing has a sea breeze thing later on here. It talks about it. Low-level winds develop in the direction of the pressure gradient force. Coriolis force is insignificant because the circulation's dimension, less than 100 miles, and lifespan, less than 12 hours, are too short for significant Coriolis deflection. Thus, the wind generally blows from a high-pressure cool surface to a low-pressure warm surface. Air rises over the warmer surface and sinks over the cooler surface. A local wind circulation is easiest to identify when synoptic scale wind patterns are weak. So that's just basically saying that without that sea breeze, land breeze thing going on, there otherwise really is no wind. It's actually creating its own wind is basically what this is saying. So local wind is essentially just little areas, and like I said, it all depends on topography. It depends on where you're at, where you live, if you're by a body of water, if you're by a mountain, it all depends. But it's kind of like its own little, what do you want to call it? It's like its own little weather system that, you know, it's not significant enough to like show up on a weather map, but it's significant enough to affect like a small area, and its lifespan, like it says here, is less than 12 hours. Like it just, you know, from day to night it can change. So local winds include sea breeze, land breeze, lake effect, valley breeze, mountain plains, wind circulation, and mountain breeze. So let's see, hazards. Local winds can produce aviation weather hazards. Turbulence and shifting surface winds are common. Clouds and precipitation, including thunderstorms, can develop in rising air over the warmer surface given sufficient moisture and lift. Sea breeze. A sea breeze, actually, I should have just went to that earlier. A sea breeze is a coastal local wind that blows from the sea to the land, caused by temperature differences when the sea surface is colder than the adjacent land. Sea breezes usually blow on relatively calm, sunny summer days. Air above the land becomes warmer, less dense than air over the water. This is because land heats up faster than water. Low-level pressure gradients develop with lower pressure over the warmer land and higher pressure over the cooler water. Low-level winds develop in the direction of the pressure gradient force. Thus, the wind blows from the water to the land. The air rises over the land, sinks over the water. Clouds and precipitation may develop in the rising air over land, with cloud dissipation over the sinking air offshore. Okay. This is kind of a good one there. One thing I was going to, so like I had like a let's see, when was it? Just over spring break, we went down to Oceanside down in California, and it was like a perfect example of this whole dynamic was going on the entire time we were there. But basically what it was causing is what happens, I mean, you can kind of see the motion here, but as you see, like where the cool air moves in over the land and then it rises up, and you can see that it forms clouds up here. Like in the middle of summer, on a nice warm day, because of the temperature and like the dew point, because of the temperature difference, those clouds normally form pretty high overhead, so they don't affect you necessarily, and they normally will form, you know, inland a little bit more than, like if you're sitting on the beach as an example, those clouds aren't normally going to form right over the beach. They're going to flow in, it raises up, and then it'll form clouds kind of a little bit inland. But if you get to like the perfect setup where, like, you know, in my example, like it's the middle of March, it's the middle of March, it's the middle kind of just it's not necessarily that warm, you know, in California, so the temperature differences are a little bit less. And so because the temperature and like the dew point is, and we'll talk about the dew point stuff later, but it basically, all it was causing, so you'd have this little breeze, and as soon as that breeze hit the shore, it was immediately lifting up, but because the air temperature was so low, it was causing those clouds to form right like on the beach. So have any of you guys ever been to, like, I don't know if anybody's been to like California in March, but a lot of times like during that time of the year, February, March, the beginning of April, you get a lot of like fog, a lot of like, and it's just right on the coast. Like if you were, it's like literally right over the beach. If you were to go a quarter of a mile inland, it's like hot and sunny, but if you go out to just like the little quarter-mile section from where like the beach starts to like just inland, maybe 2,000 feet, like literally just a little tiny stretch. It's like a cloud sitting right on the shoreline. And it's caused by this same exact thing, but it's only a certain time of year. So long story short, spring break totally sucked down there because, you know, you go down there and we had like this condo timeshare thing right on the beach, but the entire time it was just, you look out the window and it was just a cloud. Like it was cold and it was just no sun. I mean, it was just horrible. But, you know, we'd get in our car and like drive out and go get on even the freeway. I'm talking like I-5. Like if anybody's ever driven LA to San Diego, you know how close I-5 hugs the ocean, right? It's pretty close in most cases, but if you're driving through like Oceanside and Carlsbad, I mean, it's right there. I-5, where it was, I mean, that's, you can see the ocean normally. I mean, at that point, straight above the freeway was sunny. I mean, but like just right off to the right of it, it was just like a cloud. Like if you're driving on I-5 going south and you're looking to your right, you couldn't even see the beach or anything because it was just a cloud, like a wall of cloud, just like sitting there. And it sat there literally the whole week that we were there because of the same stupid little sea breeze deal. So the air rises over the land and sinks over the water. Clouds and precipitation may develop in the rising air over the land with cloud dissipation over the sinking air offshore. So it basically was this same exact cycle. It's just that if you were to take it, it was just a lot. It was a lot closer. Like it was like a tighter circle, if you could imagine. It was coming in and circulating like in a circle like this instead of a big circle like this. And that the size of this rotation is just simply going to depend on the actual temperature difference between the water and the land. The water temperature, like it was like 68 degrees, but the water temperature was like 65 degrees. So when you're only talking about like a 2-degree variance, it's not enough to like create a good enough breeze. It creates a tiny one, but if you can just kind of imagine, like the bigger the temperature difference, the more dramatic of the wind is going to be. You know, if the higher the difference is between land and water, will create a higher wind speed, which is going to create a more dramatic, like, circular effect. But when it's just a tiny little difference, it's just like, it's just going to create a little tiny bit of wind that's going to come inland, raise up, but it doesn't raise up enough, you know, and when it reaches its peak, it forms the cloud, which is so insignificant enough above that it actually is just forming a cloud on the ground is all it was doing. And then it circulates back, drops back underneath, and just repeats all day long. Sea breeze front. The horizontal discontinuity in temperature and humidity that marks the leading edge of the intrusion of cooler, moister marine air associated with the sea breeze. It often produces a wind shift and enhanced cumulus clouds along its leading edge. Cumuliform clouds may be absent if the air mass being lifted over land is dry or stable. So let's see, that's a sea breeze front, where you actually have a true high and a true low basically converging on each other. Most of these, other than just understanding how, how little things like this work, most of this is insignificant. Effects of a coastline shape. The local shape of coastline plays an important role of convection along sea breezes. A narrow peninsula or island is generally an area of strong convective development during the late morning or early afternoon. This is because sea breezes formed along opposing shores merge near the peninsula's or island center. Just kind of showing how that works. That's other than just looking at it, it's not much for us. A land breeze is a coastal breeze blowing from land to sea caused by temperature difference when the sea surface is warmer than the adjacent land. Land breezes usually occur at night and during the early morning. Same thing we already talked about. This is basically the same thing we already looked at, just reverse. Air above the land becomes cooler, denser than air above the water due to conduction. This is because land cools faster than water. Low-level pressure gradients develop with higher pressure over the cooler land and lower pressure over the warmer water. So creates the land breeze going out to sea. We already looked at that. Lake breeze is a local wind that blows from the surface of a large lake onto the shores during the afternoon and is caused by the temperature difference when the lake surface is colder than the adjacent land. The lake breeze is similar in origin to the sea breeze and is common in the Great Lakes. Both occur during the warm season, primarily spring and summer. Both are easiest to detect in light synoptic wind conditions. So yeah, this is same exact philosophy as a sea breeze. It's just a large body of water like the Great Lakes. You do get a little bit of this like with the Great Salt Lake, The most dramatic actually with the Great Salt Lake though is actually during winter when you get like lake effect snow. And I think that we cover that here. This is just showing how that works. So the cool air drops down and goes outward on both sides of the lake, just blowing out to the land. As with sea breezes, thunderstorms are favored in the upward motion branch of the lake breeze circulation. This is especially true where breezes from adjacent lakes collide. The strength of the lake breeze circulation is affected by a lake's depth. A shallow lake, like Lake Erie and Lake St. Clair, warms up rapidly and is less effective as the source of a lake breeze in summer than a deep lake, like the other Great Lakes. A valley breeze is a wind that ascends a mountain valley during the day. Air in contact with the sloping terrain becomes warmer, less dense than air above the valley. This is because the air in contact with the sloping terrain heats up faster than the air above the valley. So you do see that a little bit around here where the air likes to move up slope. Sometimes if you look out here towards what is this called? Signal Peak, right? Out here. So, is that what that mountain's called? Signal Peak? Like Pine Valley Mountain, but it's called Signal Peak, right? Anyway, I thought, yeah, I don't know.
Okay.
I've only lived here 5 years. But anyway, sometimes you'll see like clouds that just like top that thing. That's kind of what's happening with a valley breeze. So in a valley breeze situation, you have air that's traveling up the mountain, and as soon as it hits the top of the mountain, it's like it's hitting that other air that's coming up the other side of the mountain, basically. So you have, think of the mountain, you've got air moving up the back side, air moving up the front side, and it's coming up and it's converging at the top. And those two things, when they mix, creates that cloud. And a lot of times you'll call it like a cap cloud, what people will call it around here. But anyway, it gathers just right on the top, and you can just see it sitting on the top of the mountain all day long. That's just because you got two valley breezes coming up on both sides of the mountain. Let's see. It's wind that ascends a mountain valley during the day. Air in contact with the sloping terrain becomes warmer than air above the valley. This is because air in contact with the sloping terrain heats up faster than the air above the valley. So, let's see here. Let's see, that one shows it good there. Pressure gradients develop with lower pressure over the warmer sloping terrain and higher pressure over the cooler valley winds develop in the direction of the pressure gradient force. Thus, the winds blow from the valley up the mountain slopes. Air rises over the sloping terrain and sinks over the valley. Clouds and precipitation may develop over the mountain slopes. Mountain plains wind system. A mountain plains wind system is the diurnal cycle of local winds between a mountain or mountain range and the adjacent plains. This is kind of Denver-ish right here. If you think of like the frontal range out there, and then the winds coming off those mountains going out into the plains, like over the Denver airport. Sometimes you'll see really strong winds that cause Denver to have to land using the two runways that run east and west. But anyway, a mountainous plains wind system, I already read that, didn't I? During the daytime, this wind system is the equivalent of 1/2 of the valley breeze. Air in contact with the sloping terrain becomes warmer, less dense than air above the plains. This is because the air in contact with the sloping terrain heats up faster than the air above the plains. Oh, crap. Wait. What did I just do? What in the world just happened? Did I just lose that? Oh, okay. Pressure gradients develop with lower pressure over the warmer sloping terrain and higher pressure over the cooler plains. Winds develop in the direction of the pressure gradient force, thus the wind blows from the plains up the mountain slopes. There is a weak return flow aloft. Clouds and precipitation may develop in the rising air over the mountain. Oh, mountain breeze. Okay, so this is the opposite of a valley breeze. A mountain breeze is the nightly downslope winds commonly encountered in mountain valleys. Air in contact with the sloping terrain cools faster than the air above the valley. Pressure over the sloping terrain is higher than over the valleys. Cooler air over the sloping terrain is denser than warmer air over the valley. So this is just basically where the air is dropping downslope. Sometimes these winds, depending on the force, these can be very, very severe, strong winds. Is anybody from up north, like Bountiful, like anywhere along the Wasatch Front, really? Okay. Have you ever seen, like every couple of years, you'll get those massive east winds? Has anybody ever seen that? Like where you'll get those winds that come, like they're coming from the east, they come down like the Wasatch Front, like into the valley, and they like blow trees down and all that kind of stuff. Like there was like 5 or 6 years ago, there was a major one that blew trees down, like hundreds of trees, like massive, big, huge trees, and just caused all sorts of damage. Like that's sometimes associated like with these mountain breezes, basically where you get like a pressure center coming over the top of the mountain on the back side of like a high pressure, if it moves in just right. You can get those. Then they hit, and basically as they go down the mountain, the reason why they are able to grow so fast is because as the wind moves down the mountain, it gains that force of going. It's like taking a rock and rolling it down the hill. As it rolls down the hill, it's just going to speed up, speed up, speed up, and it just gains that momentum. It's kind of the same idea with winds. As they come over the top of a mountain and go down, all it does is it picks up force and strength, and as it hits the bottom, it's kind of like the microburst effect in a way. It's not, other than just it's rolling down a mountain and then kind of just spilling out into the valley, just like, like a microburst does, where it comes straight down and then rolls out. This is just coming down a mountain and then rolling out. But it can be just as strong as microburst type winds, though. Surface wind flows from the mountain down the sloping terrain into the valley, and then air rises over the valley and sinks over the sloping terrain. Let's see here. I think I'm kind of behind schedule on this thing. This is all... Okay, so this whole next part is basically covering all the states of matter. This part I might have to have you guys just kind of look at kind of on your own. This section really isn't all that big of a deal, other than just understanding the simple science behind, what causes matter to change from solid to liquids to gas. It's basically a lot of this stuff that's associated with these things we're going to be looking at and talking about later, like with, for example, like when we look at like fog and things like that, which we're going to be talking about here actually for Monday's stuff. We start talking about fog, but fog, we'll talk about how it, I can probably cover a lot of it with the fog stuff, because it's basically talking about how, when you have moisture, turning into like, where it takes on the actual liquid form as compared to like the gaseous form. So a lot of this, other than just understanding, you can read through the thing here. You can read through this and just kind of get most of this, but a lot of this is kind of just talking about, a lot more in depth that we ever really get into with, solid matter changing to liquid and to gas type stuff. So I'm just going to skip this stuff for now. Yeah, conversion tables we don't ever use. Other than reading it in here, I never hear about or talk about this Kelvin scale. So Kelvin to Fahrenheit, heat transfer. The heat transfer stuff is, a lot of that is more related to the part of that you need to know is a lot of kind of the stuff that was from yesterday's stuff, like where you have the uneven heating of the Earth's surface, and where, parts of that heat wants to transfer, which is ultimately what creates weather. That's really the biggest thing you probably need to know with that stuff. Let's see, radiation, solar radiation, conduction, so a lot of this is kind of recovering stuff that we've already talked about too, like how water, the ability for water to heat up compared to land to heat up, that it takes longer and it's slower, and then when it's cooling down it takes longer to cool than land does. This is kind of showing an example of Kansas City compared to San Francisco. The fact that San Francisco is located on the coast next to a body of water means that its yearly annual temperature average is way more moderated, and that's simply because it's next to a body of water. Water always moderates the land next to it. So, you know, San Francisco, even in winter, doesn't really, I mean, it gets colder, but not really way colder. And then in the summer, like, you know, it doesn't really get all that warm either. So, but that's all just has to do with, you know, just the body of water. And then it compares Kansas City next to nothing out there in the middle of the plains where, you know, in the winter it's way cold, in the summer it's way hot. And I think everyone for the most part understands that science. Anybody want any more in-depth than that? That's all you really need to know. Yeah, exactly. Okay, temperature inversions. This kind of goes back to the same thing we were talking about, where they get trapped underneath the high pressure systems. Water vapor. This whole section here talks about water vapor, but it's really this little figure right here is pretty much the biggest thing you really need to know and understand. It pretty much describes the entire chapter just in this one figure. So as long as you understand that how like rain develops, like, you know, if you have, as the sun heats up the water temperature increases. As it increases enough, kind of like you saw really well in that video yesterday, where it's talking about like the, what was that, the Cook Islands or what? I can't remember what islands those were to the west of Africa. But just talks about how the water temperature, you know, when the water reaches 80 degrees, it starts to evaporate, and that evaporation goes up and it forms clouds. And as it just gathers that precipitation, then the clouds, you know, will move over the land, and then they start to cool down, which causes the precipitation to drop. And then it drops the rain. The rain then gathers in lakes and streams, and it takes it back out to the ocean, and then it just repeats that same cycle. So there's not, I mean, this is a lot of the stuff, you know, you even learn in school, but there's not a lot to this, you know, other than just understanding that cycle. Water condensation, why it does. It heats up, it cools down, it evaporates, and comes down in the form of rain, snow. Anyway. This down here is talking about like the humidity. This is kind of like where you get, does anybody know like what the dew point is when you hear the term like dew point? Does anybody know what that is?
It's the point where you get condensation.
Yeah, it is. But it's also, yeah, it's basically, but the reason why it happens is because the dew point is, so it's denoted as a temperature, right? So if I'm out here, you know, like here in St. George as an example, I don't know what the current dew point is here, but in a dry environment, obviously it's going to be much less, or sorry, let's just say the difference between the actual temperature and the dew point is going to be less. So that's Teterboro. Let's just look at St. George for an example. So right now in St. George we are 17 degrees Celsius, and then if you look here in the METAR, you see this, that 17 and then that slash MO5. That's the temperature, the current temperature, and then the second one is always the dew point. So the dew point here in St. George right now is -5. That M is basically the same as a minus, just means minus. So if the temperature here dropped clear down to -5 degrees Celsius, you would then start to see condensation. You would start to see fog. You would start to see the cloud level would come down, basically. So the clouds, if you look at the level of the clouds, where you see the clouds forming, like out there, out the window there, that altitude, you can assume that that altitude where those clouds are forming, the temperature at that altitude is -5 degrees. So if you were to go out there and like measure how high those clouds are, then you would be able to, the way they figure out like how high clouds are is they can take, well, one, they can, like at the airport, they can kind of shoot like little sonar laser things up and back and kind of measure them based off of that. But another way you can do it without even having to do that at all is if you know what the dew point is. If you know the dew point's -5, you can look outside, and that's where you would get cloud formation, is at that level. So if you know that you're 17 degrees on land, then just simply do your 2 degrees per 1,000 feet, and then that's how high you can figure out clouds are without even having to have any equipment at all, other than just knowing the dew point. So when you have, basically what the dew point as a definition, it's basically where an air mass reaches its saturation point. So it's when you're in a really dry environment, you always see really high spreads of like 17 to -5. If you're in a really humid environment, if you're in the southeast or somewhere, if you're in a tropical area, the dew point is always a lot closer. But especially like in the south, and especially in places, where it's very humid, obviously, the air is saturated with water, and it doesn't take much to, sometimes you'll look up and you'll see, you usually see very low clouds, especially when you're like in tropical areas. The clouds are really usually only a couple hundred feet above you, if you're looking up. And sometimes it's not necessarily that it's like overcast, but just like, like a random cloud, even like to the extent that you see out there, you'll see them, they're really low lying because the dew point is really, compared to the temperature, is very close normally. So when the dew point and the temperature meet, if they're at the same temperature, that's where you see cloud formation on the ground, essentially. That's where you see, dew, that's where you see fog, that's where you see, just where it's really cloudy and, you can't see the mountains because there's clouds on the ground. That's basically the cloud level will come down with the dew point. Basically, as the temperature of the ground and the dew point get closer, the clouds get lower and lower and lower and lower until they're basically on the ground. That's one way to look at the dew point. But another factor that plays into like the dew point is like things like ice and stuff like that too. Like like my wife is from the south, she's from Arkansas, Missouri area, and like when her like dad comes out here and visits, and sometimes like during the winter, like if you've seen and I'm sure heard about like how they get those ice storms out in the south or in like Texas and things like that during the winter and stuff, especially, like they just get, the roads just get covered with ice. You don't ever see that happen here, right? I mean, you can, randomly you can see black ice and things like that, but like you see it a ton out there and you don't hardly ever see it here, and it's because of the dew point. It's basically dry environment, humid environment. But a lot of things that like for instance, my father-in-law, when he comes out here sometimes during the winter, and especially when we lived up north, if we would be driving up in the mountains, and he would like, he's kind of already like super like stressed type person, but he would always sit there, how the vehicles have the little temperature thing in them. We'd be driving, just going on a drive up in the mountains, and he would watch that temperature, and it would be snowing or something outside, and he would watch that thing, and it would be 36 degrees, 30, then he would see it go down, 35, 34, and he's seeing that it's snowing, And as soon as that thing hits 32, he has it in his head that means there's going to be ice. That's the freezing point, right? Everyone knows 32 degrees is freezing, right? So he's grown up, obviously, out there in the South with this idea that, like, as soon as it's freezing, that equals ice on the road. And typically out there it does, like, because the dew point, if you were to be out in the South and it would be 32 degrees, pretty good chance that the dew point also is going to be pretty close to 32 degrees. So if the dew point, and if you have precipitation and the dew point is 32 degrees and your outside air temperature is 32 degrees, that's going to mean that you'll have that saturation of the air, and you would have then, you would have precipitation on the ground, obviously, or cloud formation, which is going to create like the ice formation. But out here, even in the middle of winter, or up north, I know we don't get much here specifically, but up north, in the middle of winter, it could be snowing like crazy, and it could be 26 degrees and just snowing like crazy, and you're not going to get ice accumulation on the road because the dew point, even in the middle of winter, is still clear down at like negative, or not -5, but say like 5 or 6 degrees. So in order to get ice accumulation, you would have to have the temperature drop. So I was trying to explain this to him one day when we were up there, and it was just so like, when he was starting to freak out because it was hit 32 degrees, he's like, yo, you better be careful. It's going to start icing up. And I'm like, that's not really how it works here. And then the temperature continued to fall. Like, we were climbing up this mountain. We were going on this long mountain drive thing, and it continued to get colder, and it got down to like 27, and it was snowing pretty good, but it wasn't sticking, And so, but he just kind of had it in his head that, we were going to slide off the road, and just, it was kind of funny. But anyway, I was trying to explain to him that because of the dry environment, ice accumulation doesn't occur until the temperature has to hit the dew point in order for ice to occur, essentially, is kind of what I was trying to tell him. But where he's from, and in a humid environment, the temperature and the dew point are always really close. If you go to like San Francisco, same thing. The dew point, and anytime you're by the coast, you'll notice you usually always have low-lying clouds, because the coast, and that's the moderation. That's the ocean having that moderate effect on the land, where it keeps it cooler and it keeps the temperature closer to the dew point. And that's why you'll see fog. That's why we see a lot of flow programs in San Francisco, because the ceiling is usually rarely higher than 2,000 feet above the ground. And so the difference in that temperature on the ground and the ceiling, that's going to be the exact same difference between your temperature and your dew point, typically. So all it takes is, if the temperature, if you can look at San Francisco, just bring it up real quick, let's just see how it looks today. Okay, like today is a good example of San Fran. You see, like right now, it's a great day in San Fran. 10 miles, clear skies. But then look at the dew point temperature spread, 22 to 4. On a bad day in San Francisco, where it's foggy and you have a low ceiling and you've got a flow program, you can look at that, and you'll always see, that it's either at the dew point level or that it's within a couple of degrees, which if it's within 2 or 3 degrees, then that means that the ceiling is going to be less than 2,000 feet usually. So just kind of a little thing, just to, that's, with that kind of stuff, that's kind of what you look at more as a dispatcher with, rather than all the stuff this goes into. This is talking about, so yeah, the humidity and the dew point is just basically an air parcel's capacity to hold water. And basically, once it gets to the point that it's holding the maximum amount of water that it can hold, that's when it has to release, or it has to basically, the water will then become visible. It's kind of like a magic show in a way. It's like you can have a 1 degree spread in your cloud, in your temperature and dew point, and then as soon as those things hit each other, you'll have cloud formation right on the ground. And that's what fog is, obviously, but it's when you're looking at some of these airports we fly into that suddenly, like on the coast, that like it's fine, it doesn't need an alternate or anything like that, but you're headed there and all of a sudden it turns into a quarter-mile visibility with fog. That's because somebody, the dispatcher, probably wasn't paying attention before they sent the flight. They weren't looking at the temperature dew point spread. And a lot of times dispatchers, when they look at those two things, will add extra fuel if the temperature and dew point are really close, because they know that once the temperature and dew point meet, that you're going to have fog. So, and that can literally mean the difference. You know, like when a plane takes off, it might be 2 degrees above the dew point level, but if while they're flying there, the temperature goes down, and at night especially, obviously the temperature is always decreasing at night, but as the sun goes down, the land starts to cool, and a plane is heading somewhere, and it might not be in the forecast even, but it's the dew point, the temperature then suddenly meet while this thing's en route, and then you'll get to where you can't even land because all of a sudden it's literally like snapping your finger, you got fog, and it's just completely restricting the airport to land. So that's one thing to watch, you know, as a dispatcher when it comes to humidity, dew point stuff. Didn't quite get to where I wanted to get to. What's that?
So if you're taking the difference and then times 5,000, you're just getting.
Yeah. So if you've got a 10 degree, let's say the temperature is 20 degrees Celsius and the dew point's 10 degrees Celsius, well then your cloud level would be 5,000 feet. I mean, that's basically all that's saying. Kind of when I was going back to see if you want to be able to tell how high clouds are, that's how you can quickly tell, just without, as long as you know the dew point, then you know, and as long as you know the temperature dew point, then you'll be able to walk outside and you can say that those clouds are 5,000 feet above the ground, essentially. So that's all that does. But yeah, it's just using that 2 degrees per 1,000 feet. Didn't quite get to the clouds stuff, but you can, you know, you can get back in, and if you have time to get in there and read it, great. Both the states of matter and the cloud stuff. We do end up covering a lot of the cloud section kind of once we get down into talking about like the theory of storm systems down here, like thunderstorms, tornadoes, and basically the adverse weather type stuff and the clouds that are associated with those. So some of it will be covered, but if you have time to get in there and read those two sections, great. If not, it's not a huge deal. Most of the information from both of those sections you'll end up getting in other forms anyway, and most of the uses, dispatch uses of anything that comes from those two sections will definitely still be covered and gone over, you know, quite a bit. And as far as questions that you might see from any of those, I mean, I kind of keep track of what we cover and what we don't cover, but you know, if we don't get to it when we're supposed to, then I usually won't, you know, be trying to throw questions at you on the quizzes and stuff from it. But like I say, if you do have extra time and you want to jump in there and read those two, great, but don't put, you know, don't kill yourself over it. So, any questions on anything? Anythings? Nothing? Okie dokie. That should be it for today then.